Hello there, and welcome to Science for Sleep, a quiet place where curiosity slows down, questions soften, and science takes its time. Wherever you are right now, whether the room around you is dimly lit or completely dark, whether you're settling in for the night or simply letting the day loosen its grip, you've arrived at a gentle pause. Tonight we're going to explore something that sounds empty, silent, and still at first glance, but turns out to be anything but. We're going to talk about nothing, or more precisely, we're going to talk about the quantum vacuum. At first, that phrase might sound a little intimidating, like something pulled straight from a chalkboard covered in equations. But there's no need to brace yourself. This isn't a race through complicated math or a demand to understand every technical detail. Instead, it's a slow walk through an idea that sits quietly beneath everything you see, touch, and experience. The quantum vacuum isn't an exotic corner of physics reserved for particle accelerators and research papers. It's everywhere. It's here in the space between you and the walls of the room. It's in the gap between atoms in your body. It's even drifting through the vast stretches of space between stars. And strangely enough, it may be one of the most active, restless things in the universe. Before we go any further, let me ask you something simple. Where are you listening from tonight? Are you at home, tucked into bed, or maybe resting on a couch as the day fades out? And what time is it where you are right now? It's fitting to ask, because just like time, the idea of nothingness feels familiar until we stop and look closely. The moment we do, it starts behaving in unexpected ways. If you find this kind of slow, thoughtful exploration soothing, or if it helps your mind unwind after a long day, I'd be grateful if you gave the video a like or subscribe to the channel. It helps this calm little corner reach others who might also be looking for a quieter way to think about the universe. But for now, there's nothing you need to do at all. You don't need to remember facts or follow along actively. Just let the ideas drift past at their own pace. When most of us hear the word vacuum, we picture emptiness, a region where nothing exists. No air, no particles, no sound. Maybe something like outer space, vast and silent, or the inside of a machine designed to suck everything away. In everyday life, a vacuum is defined by what it lacks. It's the absence of stuff. And for a long time, that was exactly how scientists thought about it too. Empty space was just that. Empty. A background. A blank stage where matter moved around and events unfolded. In classical physics, this idea made perfect sense. If you removed all the particles from a region, what you were left with was nothing at all, no energy, no activity, no structure. Space itself was simply a container, and the vacuum was the container with nothing inside it. This view worked remarkably well for describing motion, gravity, and the behavior of everyday objects. It felt intuitive. After all, if you clear a room of furniture and people, the room doesn't start doing anything on its own. It just sits there, quietly being empty. But as physics moved into the 20th century and began probing smaller and smaller scales, this comforting idea of emptiness started to unravel. When scientists began studying atoms and the particles inside them, they discovered that the universe at its most fundamental level doesn't behave like solid objects moving through empty space. Instead, it behaves more like a collection of fields, rippling and interacting everywhere at once. And those fields, as it turns out, never truly switch off. In quantum physics, the vacuum is not defined as the absence of everything. Instead, it's defined as the lowest possible energy state of these fields. That might sound like a small difference, but it changes everything. Because in the quantum world, having the lowest possible energy does not mean having zero energy. It means there is still a baseline level of activity that cannot be removed, no matter how hard you try. Imagine trying to calm the surface of a lake. You might wait for the wind to die down, for the waves to fade until the water looks perfectly still. But even then, if you could zoom in close enough, you'd still see tiny ripples, vibrations, and movements caused by temperature, molecular motion, and interactions beneath the surface. The quantum vacuum is a bit like that. Even when all particles are removed, even when everything is cooled to near absolute zero, there is still motion. Not because something is disturbing it from the outside, but because complete stillness is not allowed. One of the reasons for this is a fundamental rule of quantum mechanics known as the uncertainty principle. In simple terms, it tells us that certain properties of a system, like position and momentum, cannot both be known with perfect precision at the same time. There is always a bit of uncertainty, a kind of built-in blur. This uncertainty isn't due to bad measurements or limited instruments. It's woven into the fabric of reality itself. Because of this, quantum fields can never be perfectly quiet. If they were, their energy and behavior would be known exactly, and that's not permitted. So instead they fluctuate, they jitter, they momentarily borrow energy and then give it back. These fluctuations are not just theoretical curiosities, they have real, measurable effects, and they happen everywhere, all the time. This leads us to one of the most surprising ideas in modern physics. Empty space is full of activity. Not activity in the everyday sense of objects moving around, but activity in the form of fleeting changes in energy and fields. These changes are so subtle and so brief that they don't show up in ordinary experience. You don't feel them, you don't see them, but they are there, quietly shaping how the universe behaves. Physicists often describe this restless behavior in terms of virtual particles. These are not particles you can detect directly, or capture in a detector. They don't hang around long enough for that. Instead, they appear and disappear almost instantly, popping in and out of existence within the limits allowed by quantum uncertainty. They're more like temporary disturbances than actual objects, but their effects add up. This might sound strange, or even a little unsettling. How can something appear out of nothing? How can energy exist where there is supposed to be emptiness? The answer lies in how we define nothing in the first place. In quantum physics, nothing is not a void. It's a state governed by rules, constraints, and structure. The vacuum is not the absence of reality. It's a particular way reality organizes itself when it is settled as low as it can go. One way to think about it is to imagine a perfectly quiet room. No music, no voices, no movement. But even in that room, there's still a faint hum from electrical systems, the soft rush of air through vents, the subtle creaks of the building as temperatures change. Absolute silence is incredibly difficult to achieve, and absolute nothingness turns out to be even more elusive. What's especially fascinating is that the quantum vacuum is not the same everywhere. Different fields contribute different kinds of fluctuations. Some are associated with the electromagnetic forces, others with particles like electrons or quarks. Each field has its own baseline behavior, its own version of restlessness. Together they form a complex dynamic background that underlies everything else. This background is so fundamental that many physicists now think of particles not as standalone objects, but as excitations of these underlying fields. In that picture, what we call a particle is just a localized ripple, a small vibration in a field that otherwise fills all of space. When the field is calm, we call it the vacuum. When it's excited, we call it matter or energy. But it's the same underlying thing. That idea quietly reshapes how we think about existence itself. Instead of a universe made of solid things moving through empty space, we have a universe made of continuous fields, always present, always capable of activity. The vacuum is not the stage, it's part of the play. At this point, it's tempting to imagine the quantum vacuum as chaotic or noisy, like a storm of random fluctuations constantly churning beneath reality. But that's not quite right either. While it is active, it's also highly structured. The fluctuations follow strict statistical rules. They average out over time and space. They don't lead to obvious instability or disorder. In fact, they help create stability. Without the quantum vacuum behaving the way it does, atoms wouldn't hold together properly. Forces wouldn't behave the way we expect. Even the properties of empty space, like its ability to transmit light, depend on these underlying fluctuations. In a very real sense, the vacuum helps define what's possible in the universe. And this is where the idea begins to shift from curious to quietly profound. The emptiness between things is not just a passive gap. It's an active participant. It influences how particles interact, how forces propagate, and how the universe evolves over time. It's subtle, patient, and usually unnoticed, but it's always there. When you hear the word vacuum, you don't need to picture a void or a blank. You can picture a quiet field at rest, gently fluctuating, full of potential. Not busy in an obvious way, not dramatic or loud, but never truly still. And as your thoughts slow down and your attention softens, it might be comforting to know that even in the quietest places imaginable, there is still a gentle hum of activity. A reminder that stillness and motion aren't opposites, and that even nothing, when you look closely enough, has something to say. For most of human history, the idea of nothing seemed simple. If you took something away, and then took everything else away too, whatever remained was nothing. No objects, no substance, no activity. Just absence. It felt like a concept that didn't need much explanation. After all, we deal with empty spaces every day. An empty cup, an empty room, a quiet pause in a conversation. Nothing feels familiar, even comforting at times. But the deeper science has looked into the universe, the more that comfortable idea has started to unravel. To understand why the notion of nothing refuses to behave the way we expect, it helps to begin with how deeply rooted the idea of emptiness is in human thinking. Long before laboratories and particle detectors, philosophers argued about whether true nothingness could even exist. Some believed that empty space was impossible, that nature always filled every gap. Others imagined voids separating objects, places where matter simply wasn't present. These debates weren't just abstract. They shaped how people understood motion, causation, and even existence itself. In ancient times, thinkers like Aristotle rejected the idea of a vacuum entirely. He argued that empty space couldn't exist because there would be nothing to define motion within it. For Aristotle, space was always filled with substance, and any attempt to create a void would be immediately undone by nature rushing in to fill it. This idea persisted for centuries, not because it was proven correct, but because it fit comfortably with everyday experience. Air rushes into empty containers, liquids fill gaps, emptiness seems unstable. It wasn't until much later, with the rise of experimental science, that people began to seriously challenge this view. In the 17th century, experiments with air pumps showed that it was possible to remove air from a sealed container, creating something close to a vacuum. Objects behaved differently in this space. Flames went out. Sounds disappeared. The absence of air had real, observable consequences. This seemed to confirm that empty space could exist after all. Classical physics embraced this idea. Space became a passive backdrop, a container in which matter moved and forces acted. If you removed all particles from a region, what remained was empty space, nothing more. It had no properties of its own. It didn't push or pull. It didn't vibrate or fluctuate. It simply was, or rather, it simply wasn't anything at all. For a while, this view worked remarkably well. Newton's laws described motion through empty space with extraordinary accuracy. Planets moved through the vacuum between stars. Objects fell and collided without any need for space itself to play an active role. The universe, in this picture, was a stage. Matter and energy were the actors. The vacuum was the silence between lines. But as physics began to probe smaller scales, cracks started to appear. Atoms, once thought to be solid and indivisible, turned out to be mostly empty space themselves. Electrons didn't orbit nuclei like tiny planets. They existed in diffuse clouds of probability. Even at this level, emptiness wasn't behaving the way intuition suggested. The closer scientists looked, the less solid everything became. Then came quantum mechanics, and with it, a fundamental shift in how emptiness was understood. In quantum theory, particles are not isolated objects moving through a void. They are excitations of underlying fields. These fields exist everywhere, even in regions where no particles are present. You can remove every detectable particle from a region of space, but you cannot remove the fields themselves. They are built into the structure of reality. This is where the idea of nothing begins to break down in a very precise way. In quantum physics, the vacuum is defined as the state where all fields are in their lowest possible energy configuration. Not zero energy, lowest possible. That distinction matters more than it might seem at first. In everyday life, the lowest energy state of something often means complete rest. A ball at the bottom of a hill isn't going anywhere. A pendulum hanging straight down isn't swinging. It feels natural to assume that the lowest energy state is perfectly still. But quantum systems don't allow perfect stillness. One reason for this is the uncertainty principle. It places strict limits on how precisely certain pairs of physical quantities can be known at the same time. Energy and time are one such pair. If a system's energy were exactly zero and perfectly fixed, it would violate these limits. So instead, quantum systems retain a small amount of residual energy, even in their ground state. This residual energy is known as zero-point energy. It is not energy you can extract or use to do work in the conventional sense. It's more like a baseline hum that cannot be turned off. Every quantum field carries this zero-point energy, and because fields exist everywhere, so does this baseline activity. This means that the vacuum is not empty in the classical sense. It is filled with fields quietly fluctuating around their lowest energy state. These fluctuations are not optional. They are required by the rules of quantum mechanics. Trying to eliminate them would be like trying to draw a perfectly sharp line with a pencil that has a finite width. The fuzziness is built in. These fluctuations manifest in various ways. One of the most commonly discussed is the appearance of virtual particles. These are temporary disturbances in fields that behave somewhat like particles, but only for extremely short periods of time. They cannot be directly observed, but their effects can be measured indirectly. It's important to be clear about what virtual particles are and are not. They are not tiny objects popping in and out of existence in the way science fiction sometimes suggests. They are mathematical features of how quantum fields behave. When fields fluctuate, the equations describing them resemble processes involving particles. We call these features virtual particles because they appear in calculations, even though they cannot be isolated or detected like real particles. Despite their fleeting nature, these virtual processes have real consequences. They slightly alter the behavior of forces. They shift energy levels in atoms. They contribute to measurable effects that have been confirmed experimentally. In other words, the vacuum does things. One of the earliest hints that empty space might not be empty came from studies of atomic behavior. When physicists calculated the energy levels of electrons in atoms, they found small discrepancies between theory and experiment. These discrepancies were eventually traced back to interactions between electrons and the vacuum fluctuations of electromagnetic fields. The supposedly empty space around the atom was subtly influencing its internal structure. Another clue came from particle physics. When particles interact, the strength of those interactions depends on the surrounding vacuum. The vacuum can polarize, much like a material medium responds to electric fields. This polarization affects how forces propagate through space. Even the value of fundamental constants depends in part on vacuum behavior. All of this points to a profound conclusion. Empty space is not a neutral background. It has structure. It has properties. It responds to the presence of matter and energy. It shapes the behavior of the universe in quiet but fundamental ways. This realization forces a re-examination of what we mean by nothing. In everyday language, nothing means the absence of anything at all, but in physics, nothingness is defined relative to a framework. A vacuum is empty of particles but not empty of fields. It is devoid of excitations but not devoid of existence. Even that definition has layers. The vacuum of one theory is not necessarily the vacuum of another. In quantum field theory, different vacua can exist depending on conditions. A vacuum in one region of space might not be the same as a vacuum in another if fields settle into different configurations. This idea plays a role in cosmology and the study of the early universe, where the vacuum itself may have changed over time. The refusal of nothing to stay empty also appears when gravity enters the picture. According to general relativity, energy and mass influence the curvature of space-time. If the vacuum contains energy, even in a subtle form, then it should gravitate. It should have an effect on the expansion and shape of the universe. This leads to one of the most puzzling problems in modern physics. When scientists calculate the expected energy density of the quantum vacuum, they get a value that is staggeringly large. If this energy gravitated in the way we expect, the universe would either collapse or expand violently. Instead, the observed effect is tiny. This mismatch between theory and observation is known as the cosmological constant problem, and it remains unsolved. The existence of this problem highlights just how incomplete our understanding of nothingness still is. We know the vacuum has energy, we know it fluctuates, we know it influences physical processes, but we do not yet know why its large predicted energy doesn't overwhelm the universe. From a conceptual standpoint, this situation is deeply unsettling and quietly fascinating. The thing we once thought of as absence turns out to be one of the most mysterious components of reality. Nothing is not simple. It is layered, constrained, active, and subtle. This complexity also challenges the way we think about existence itself. If empty space has properties, energy, and influence, then the line between something and nothing becomes blurred. The vacuum is not a thing in the usual sense, but it is not nothing either. It occupies a strange middle ground, defined more by what it can do than by what it is made of. There is a certain humility in this realization. It reminds us that intuition, shaped by everyday experience, is not always a reliable guide at the deepest levels of nature. Concepts that feel obvious, like emptiness, can behave in unexpected ways when examined closely. It also invites a quieter perspective. The universe does not require constant motion or visible activity to be alive with processes. Even in the absence of particles, even in the deepest reaches of interstellar space, there is a gentle undercurrent of behavior. Fields fluctuate, energy shifts, possibilities ripple quietly beneath the surface. As these ideas begin to settle, it becomes easier to see why physicists no longer treat the vacuum as a passive backdrop. It is an active participant in the unfolding of reality. It shapes forces, influences particles, and may even play a role in the fate of the cosmos itself. And yet, despite all this activity, the vacuum remains elusive. Its effects are subtle. Its presence is indirect. It does not announce itself loudly. It operates in the background, steady and patient, revealing its nature only when experiments are refined enough to notice its touch. This quiet persistence is part of what makes the quantum vacuum such a compelling subject. It challenges expectations without drama. It refuses to be empty, not with explosions or chaos, but with a steady, unavoidable presence. It's enough to rest with the simple but profound realization that emptiness is not what it seems, that removing everything does not leave behind a blank. It leaves behind a quiet, restless state, shaped by rules that prevent true stillness. And as these thoughts drift by, there's no need to hold on to them tightly. They can remain impressions rather than conclusions. The universe does not rush, and neither does this story. The idea of nothing will continue to unfold, gently refusing to stay empty. At first glance, empty space seems like the most well-behaved thing imaginable. It doesn't argue, it doesn't move objects around on its own, and it certainly doesn't look like it's doing anything dramatic. If something strange happens, we usually blame matter, energy, or forces acting between things. Empty space, by contrast, feels like the quiet bystander. But as physics has learned to listen more carefully, that quiet has turned out to be full of interruptions. And this is where empty space begins to misbehave, not loudly or chaotically, but in ways that are subtle, persistent, and impossible to ignore once noticed. To understand what misbehavior even means in this context, it helps to remember how strongly classical physics trained us to trust empty space. In that older picture, space had no personality. It didn't react, it didn't fluctuate, it didn't push back. If two objects interacted, space was simply where the interaction happened, not something involved in it. That assumption ran deep. Even when early experiments showed that light could travel through a vacuum, space itself was still treated as a neutral corridor, not an active medium. The first signs of trouble appeared when physicists began to calculate things with increasing precision. As measurements improved, tiny discrepancies began to show up. Not dramatic failures, not broken theories, but small mismatches between prediction and observation. At first, these differences could be dismissed as experimental error, but as instruments became more sensitive and calculations more refined, the discrepancies persisted. Something was nudging the results, and it wasn't coming from any visible particle. One of the earliest clues came from atomic spectra. When electrons in atoms jump between energy levels, they emit or absorb light at very specific frequencies. Quantum theory predicted these frequencies with remarkable accuracy, and yet when measured carefully, some energy levels were slightly shifted. These shifts were tiny, but consistent. They showed up again and again, no matter how carefully the experiments were repeated. Eventually, physicists traced the source of these shifts to interactions between electrons and the electromagnetic vacuum. The supposedly empty space surrounding the atom was influencing the electron's behavior. The vacuum wasn't just there, it was doing something. This phenomenon, later known as the Lamb shift, was one of the first clear demonstrations that empty space could not be treated as inert. The electromagnetic field, even in its lowest energy state, fluctuates. These fluctuations subtly modify the forces acting on charged particles. The result is a measurable change in atomic energy levels. Empty space had reached into the atom and adjusted its structure ever so slightly. That realization opened the door to a broader question. If vacuum fluctuations could influence atomic behavior, what else might they be affecting? The answer, it turned out, was quite a lot. One of the most striking examples of vacuum misbehavior involves force without contact. Imagine placing two perfectly smooth, uncharged metal plates extremely close together in a vacuum. Classical physics would predict nothing unusual. No electric force, no magnetic force, no air pressure, just two inert objects floating near each other. But when this experiment was actually performed, something unexpected happened. The plates were drawn together. Not strongly, not violently, but measurably. There was a force pulling them inward, even though no known classical force could account for it. This effect arises because the quantum vacuum behaves differently in confined spaces. Between the plates, only certain wavelengths of vacuum fluctuations are allowed. Outside the plates, a wider range of fluctuations exists. This imbalance creates a pressure difference, pushing the plates together. The vacuum, constrained by boundaries, responds by exerting force. What makes this especially strange is that nothing tangible is flowing or pushing in the usual sense. There is no substance pressing on the plates. The force arises purely from the altered behavior of empty space itself. The vacuum is sensitive to geometry. Change the boundaries, and its behavior changes. This kind of sensitivity would be deeply surprising if space were truly nothing. But once space is understood as filled with quantum fields, the behavior becomes inevitable. Fields respond to constraints. Even in their lowest energy state, they are not static. Restrict their possible modes of fluctuation, and the energy distribution changes. The vacuum adjusts, and that adjustment can move objects. Another way empty space misbehaves is through its influence on particle interactions. In quantum field theory, forces are mediated by fields, and those fields interact with the vacuum. When a charged particle exists in space, it polarizes the vacuum around it. Virtual particle-antiparticle pairs momentarily appear and affect how the electric field propagates. This means that the force between two charges is not simply a direct interaction. It is filtered through the vacuum. The strength of the force depends on how the vacuum responds. At very small distances, this response changes slightly, leading to corrections in the force law. Once again, empty space refuses to stay neutral. These vacuum effects are not limited to electromagnetism. Other fields, associated with different forces, also fluctuate. Each contributes its own background activity. The combined effect is a vacuum that is rich with structure, even though it contains no particles in the usual sense. This misbehavior becomes even more apparent when acceleration enters the picture. According to quantum theory, what counts as a vacuum can depend on the observer. An observer moving at constant speed through space will describe a particular vacuum state. An observer accelerating through that same region may describe it differently. From the perspective of an accelerating observer, empty space can appear warm. Not metaphorically warm, but literally filled with a thermal bath of particles. This phenomenon arises because acceleration changes how vacuum fluctuations are perceived. What one observer calls empty, another experiences as populated. This doesn't mean particles magically appear in an absolute sense. It means that particle concepts depend on how motion and time are defined. The vacuum is not an objective, universal state. It is relational. Its properties depend on context. This idea further undermines the notion of emptiness as a fixed baseline. Empty space behaves differently depending on motion, boundaries, and fields. It adapts. It responds. It misbehaves according to rules that are subtle but precise. Gravity adds yet another layer to this story. According to general relativity, space-time is not a rigid container. It bends and curves in response to energy and mass. If the vacuum contains energy, even as a baseline fluctuation, then it should contribute to this curvature. On cosmic scales, this contribution becomes significant. Observations of the universe's expansion suggest that empty space has a small but persistent energy density. This energy appears to drive the accelerated expansion of the universe. Space itself is stretching faster and faster, not because of matter pushing outward, but because the vacuum seems to be supplying energy. This behavior is perhaps the ultimate example of empty space refusing to behave. The vacuum is not only active on microscopic scales, it may be shaping the large-scale evolution of the cosmos. The emptiness between galaxies is not just passive distance, it is part of the engine driving cosmic history. What makes this especially unsettling is how poorly theory and observation align. When physicists calculate the expected energy of the vacuum using quantum field theory, they arrive at values that are enormously larger than what is observed. If those calculations were taken at face value, the universe would expand catastrophically. Instead, the observed effect is small, gentle, and steady. This mismatch suggests that something profound is missing from our understanding. Either our calculations are incomplete, or our assumptions about how vacuum energy interacts with gravity are flawed. In either case, empty space is behaving in a way we do not yet fully understand. Despite this uncertainty, one thing is clear: the vacuum is not an afterthought. It is not a leftover concept defined by subtraction. It is a central feature of reality with measurable consequences. What's striking is how quietly this misbehavior operates. There are no flashing lights, no dramatic signals. The vacuum influences things gently through shifts, corrections, pressures, and long-term trends. It works in the background, shaping outcomes without drawing attention to itself. This subtlety makes it easy to forget. Everyday life offers no obvious clues. Chairs don't drift together. Rooms don't collapse inward. Space feels empty enough to be empty. And yet, when experiments are designed carefully enough, the vacuum reveals its presence. There's a certain irony here. The more completely we remove matter from a region, the more clearly the vacuum's behavior can be seen. By stripping space of everything obvious, what remains becomes more noticeable. This challenges a deeply ingrained habit of thought. We're used to explaining behaviour by pointing to things, objects, particles, substances. When something happens, we ask what caused it. With the vacuum, the cause is not a thing, but a state, a condition governed by rules rather than contents. This shift in perspective is not easy. It requires letting go of the idea that reality is made only of objects. Instead, it suggests that relationships, constraints, and baseline conditions matter just as much. The misbehaviour of empty space also blurs the boundary between existence and non-existence. If empty space can exert force, influence motion, and shape cosmic evolution, then calling it nothing feels increasingly misleading. It may lack particles, but it does not lack impact. At the same time, it would be wrong to think of the vacuum as a hidden substance or medium in the old sense. It is not ether. It does not provide a preferred frame of rest. Its properties emerge from quantum fields and their interactions, not from a material filling space. This balance between activity and absence is part of what makes the quantum vacuum so difficult to grasp intuitively. It behaves, but not like a thing. It influences, but not by pushing in a classical way. It exists, but not as an object. As these ideas settle, it becomes clear why physicists describe the vacuum as restless. Not busy, not chaotic, but never completely still. Always fluctuating within limits, always responding to context. This restlessness does not mean instability. On the contrary, it provides a kind of stability. The vacuum defines what counts as normal. It sets baselines for energy, determines how forces propagate, and anchors the behaviour of fields. Its misbehaviour is structured, constrained, and consistent. In that sense, empty space is misbehaving only relative to our expectations. It is not breaking rules. It is following them faithfully. The surprise comes from discovering that the rules are richer than we imagined. As attention continues to shift toward the vacuum itself, new questions naturally arise. If empty space can push objects, shape forces, and influence cosmic expansion, what else might it be doing quietly in the background? How deep does this behaviour go, and are there limits to how strange emptiness can become? If empty space were truly silent, truly calm, then once we stripped away matter and energy, there would be nothing left to notice. No movement, no variation, no hint that anything at all was happening. But as quantum physics keeps revealing, the vacuum does not sit quietly. It murmurs, it trembles, it produces fleeting signs of activity that never quite settle into permanence. And while these signs are subtle, almost shy, they are constant. This is where the image of a vacuum that bubbles and whispers begins to feel less like metaphor and more like an accurate description of what physics observes. To understand this behaviour, it helps to shift away from the idea of particles as the most fundamental elements of reality. In quantum field theory, particles are not primary, fields are. Each type of particle corresponds to a field that exists everywhere in space. Even when no particles are present, the fields remain. They cannot be removed. They define what the vacuum is. These fields are not static backgrounds. They behave more like flexible systems that can vibrate, stretch, and fluctuate. Even when a field is in its lowest possible energy state, it cannot be perfectly still. The uncertainty principle prevents that. If a field's value were completely fixed everywhere, with no variation at all, it would violate the basic rules that govern quantum behaviour. So instead, the field fluctuates around its lowest energy configuration. These fluctuations are not dramatic waves sweeping across space. They are tiny, localized, momentary variations, small rises and falls in energy that appear and disappear almost instantly. They do not accumulate into visible motion. They average out over time, but they are always present. This constant low-level activity is what gives the vacuum its bubbling quality. It is not bubbling like boiling water, with large energetic motions. It is bubbling in the sense that it is never perfectly smooth. There are always tiny disturbances, like microscopic eddies in an otherwise calm sea. Physicists sometimes describe this in terms of pairs of virtual particles appearing and disappearing. Again, this language can be misleading if taken too literally. Nothing is popping into existence from absolute nothingness and then vanishing again. What's happening is that the fields themselves fluctuate in ways that resemble particle-like behavior for very brief moments. These fluctuations are allowed as long as they respect the uncertainty principle. Energy can fluctuate by a certain amount if it does so only for a sufficiently short time. The larger the fluctuation, the shorter its duration must be. This creates a dynamic balance. Small fluctuations can last a bit longer. Large ones vanish almost immediately. The result is a vacuum filled with fleeting activity that never quite settles. It is restless but disciplined, active but constrained, always in motion, but never exploding into chaos. What makes this even more interesting is that these fluctuations are not uniform in their effects. Some of them interact with matter in measurable ways, others influence forces. Still, others appear to contribute to large-scale phenomena that only become apparent over cosmic distances and times. One way to visualize this is to imagine the vacuum as a surface under constant tension. Not tension in the emotional sense, but physical tension, like a stretched fabric. Even when nothing presses on it, the fabric still vibrates slightly. Tiny oscillations ripple through it, even in the absence of external disturbance. Now imagine placing something on that surface, a particle, a boundary, a gravitational field. The pattern of vibrations changes. Some oscillations are suppressed, others are enhanced. The background activity reorganizes itself in response. The vacuum whispers back. These whispers are not sounds. They are effects, slight shifts in energy levels, tiny forces, minuscule corrections to equations. They don't announce themselves loudly. They show up as details that refuse to go away when calculations are done carefully. One of the most striking aspects of this bubbling vacuum is how it responds to constraints. When space is confined or shaped in particular ways, the allowed fluctuations change. Certain wavelengths are permitted, others are not. This alters the energy distribution of the vacuum itself. This sensitivity to geometry is deeply non-classical. In classical physics, empty space does not care about shape. Put walls around it, and nothing changes unless something inside interacts with the walls. But in quantum physics, the vacuum itself responds to boundaries. This is why carefully arranged objects can feel forces from empty space. The vacuum between them is not the same as the vacuum outside them. The difference produces pressure. The vacuum pushes, not because something is inside it, but because of what it is allowed to do. What's remarkable is that this pushing arises without any exchange of particles in the usual sense. There is no stream of objects colliding with surfaces. There is only a difference in the pattern of fluctuations, and that difference is enough. This tells us something important. The vacuum is not just a passive ground state. It has internal structure. It has degrees of freedom. It can be altered, shaped, and influenced. And when it is, it responds. The whispering aspect of the vacuum becomes apparent when we consider how subtle these effects are. Vacuum fluctuations do not dominate everyday experience. They do not overwhelm classical forces. They correct them. They modify them slightly, often by tiny fractions that only become visible under extreme conditions. In atomic physics, these whispers show up as energy shifts. In particle physics, they appear as corrections to interaction strengths. In cosmology, they may appear as a slow, steady influence on the expansion of the universe. Each context reveals a different aspect of the same underlying behavior. The vacuum is active everywhere, but its influence depends on scale, environment, and sensitivity. Another layer of this whispering emerges when temperature is considered. At absolute zero, thermal motion disappears, but vacuum fluctuations remain. They are not caused by heat. They are not random noise. They are intrinsic to the fields themselves. This distinction matters. Thermal fluctuations fade as systems cool. Vacuum fluctuations do not. They persist even in the coldest, emptiest regions imaginable. Even in deep intergalactic space, far from stars and galaxies, the vacuum continues to fluctuate. In that sense, the vacuum provides a kind of baseline motion. Not motion through space, but motion of space's underlying fields. It is a quiet activity that does not depend on external energy sources. It is simply how the universe is built. The idea that empty space whispers also connects to how information and causality are constrained. Vacuum fluctuations do not allow information to travel faster than light. They do not enable free energy extraction. They respect the fundamental limits imposed by relativity and quantum mechanics. This is important because it prevents the vacuum from becoming a source of paradoxes. Despite its activity, it does not allow perpetual motion machines. It does not violate conservation laws in any exploitable way. Its bubbling is self-contained, balanced, and regulated. Still, the fact that these fluctuations exist at all raises deep questions. Why does the vacuum have this particular structure? Why do fields exist everywhere? Why is the lowest energy state not perfectly empty? Some physicists suspect that the answers lie in deeper theories not yet fully understood. The vacuum we describe may itself be an emergent feature of something even more fundamental, or it may be the most basic level of description we can reach. What's clear is that the vacuum we observe is not accidental. It follows precise mathematical rules. Its fluctuations can be calculated. Their effects can be predicted. When experiments are sensitive enough, those predictions are confirmed. This reliability is what transforms the idea of a whisper into something scientific. These are not poetic murmurs. They are consistent signals embedded in the behavior of reality. There is also a quiet symmetry to this picture. The vacuum is active, but not directional. Its fluctuations do not prefer one outcome over another on average. Over time, they balance out. This statistical neutrality is part of what allows the universe to remain stable. If the vacuum's activity were biased or cumulative, it could drive runaway effects. But instead, it hums steadily, providing a background texture without overwhelming the structures built upon it. This texture becomes especially important when considering how particles acquire properties. In some theories, interactions with the vacuum help determine masses and interaction strengths. The vacuum is not just where particles exist, it participates in defining what those particles are. In that sense, the vacuum is not empty space waiting to be filled. It is a condition that shapes what filling even means. This perspective subtly alters how existence is framed. Instead of thinking in terms of objects floating in nothingness, it becomes more accurate to think of patterns emerging from an underlying field-rich environment. The vacuum is not absence, it is a foundation, and yet this foundation does not assert itself aggressively. It whispers, it nudges, it corrects, it responds. It leaves room for structure to form without dictating every detail. This quietness is part of why the vacuum remained invisible for so long. Only when physics became precise enough to notice its effects did its presence become undeniable. As instruments improved and theories deepened, the vacuum slowly revealed its voice, not through loud anomalies, but through consistent, subtle deviations that refused to disappear. Listening to these whispers requires patience. It requires accepting that the most important features of reality may not announce themselves clearly. They may require careful attention, refined tools, and a willingness to question assumptions. The bubbling vacuum challenges the assumption that stillness equals emptiness. It shows that even at rest there can be activity. Even in silence there can be structure. This idea can feel unsettling at first. It undermines a simple mental picture. But it also offers a kind of reassurance. The universe is not held together by fragile stillness. It is supported by a dynamic balance that persists even in the absence of matter. If the vacuum bubbles and whispers everywhere, how do these fluctuations relate to the particles we observe? How do they contribute to forces, to stability, to change? For now, it's enough to remain with the image of empty space that is never quite empty. A background that hums softly, a foundation that moves without travelling, a presence that does not intrude, but never disappears. As thoughts slow and the day recedes, this idea doesn't need to be held tightly. It can sit quietly in the mind, like a low, steady sound just at the edge of hearing. The vacuum bubbles, the vacuum whispers, and without ever raising its voice, it continues to shape everything that follows. When physicists first began talking about virtual particles, the language they used made the idea sound strange, almost whimsical. Particles appearing out of nowhere, existing briefly, then vanishing again without leaving a trace. To anyone outside the field, it sounded suspiciously like fantasy. And even within physics, the concept was treated carefully, because it was never meant to be taken too literally. Virtual particles are not tiny objects darting in and out of reality like fireflies. They are something quieter, subtler, and in many ways more elusive. They pass through our equations and our understanding the way daydreams pass through the mind. Present, influential, but never fully grasped. To make sense of virtual particles, it helps to remember that quantum physics does not describe the world in terms of solid objects with precise trajectories. It describes probabilities, interactions, and fields. When physicists calculate how particles interact, they use mathematical tools that break complex processes into simpler pieces. In those calculations, certain terms appear that behave as if particles briefly exist between interactions. These terms are what we call virtual particles. They are not particles you can isolate, capture, or detect directly. You cannot build a detector to watch a virtual particle pass by. If you try, it stops being virtual. What you detect instead are real particles, excitations that persist long enough to be observed. Virtual particles exist only as part of interactions. They are internal features of processes, not standalone entities. Despite this, their influence is real. Virtual particles contribute to forces, to energy shifts, to measurable effects that experiments confirm with astonishing precision. They are like intermediate steps in a calculation that cannot be removed without breaking the result. Even though they are not directly observable, their fingerprints are everywhere. One way to approach this idea is to think about how forces work in quantum field theory. In classical physics, forces are often described as direct interactions. One object pushes or pulls another. In quantum physics, forces arise from interactions between fields. When two charged particles repel each other, for example, the interaction is described in terms of the electromagnetic field. In calculations, this interaction can be represented as an exchange of virtual photons. These photons are not real light particles travelling between charges. They do not obey the same rules as real photons. They do not have to have the same energy and momentum relationships. They exist only within the interaction itself. This representation is a bookkeeping tool, but it is a powerful one. It allows physicists to calculate forces with extraordinary accuracy. The fact that this tool works so well suggests that virtual particles capture something genuine about how interactions unfold, even if they are not physical objects in the usual sense. The uncertainty principle plays a key role here. It allows energy to fluctuate temporarily, as long as those fluctuations are short-lived. This does not mean energy is being created from nothing in a way that violates conservation laws. Over longer timescales, energy is conserved, but over very short intervals the system can explore a range of possibilities. Virtual particles arise from these fleeting possibilities. They are allowed to exist briefly as part of an interaction, then fade away before they can be directly observed. They are not violations of physical law, they are expressions of it. This is where the comparison to daydreams becomes useful. A daydream does not replace reality. It does not persist or have independent existence. But it can influence your thoughts, your emotions, your next actions. It passes through awareness, leaves a trace, then dissolves. Virtual particles behave in a similar way within the structure of quantum interactions. They pass through calculations, influence outcomes, and disappear. They are never fully present, but never entirely absent either. The vacuum is where this becomes especially important. In empty space, there are no real particles, but the fields remain. Those fields fluctuate, and those fluctuations can be described in terms of virtual particles interacting with each other and with real particles that happen to be nearby. This means that even in the absence of matter, the vacuum is filled with potential interactions. Virtual particles are constantly being invoked in the language of the theory to describe these fluctuations. They are not objects swimming in space, but they are a way of capturing how the vacuum behaves. One of the most striking consequences of this is that the properties of particles are not fixed in isolation. An electron, for example, is not just a bare object with a fixed charge and mass. It is surrounded by a cloud of virtual processes. Virtual particles influence its effective charge, its energy, and how it interacts with other particles. This cloud is not something you can see or touch. It is a description of how the electron interacts with the vacuum around it. The vacuum is not empty. It responds to the presence of the electron. Virtual particles mediate that response. As a result, the electron you measure in an experiment is not the same as the hypothetical electron you would have if the vacuum were truly empty and inactive. The vacuum dresses the particle, altering its behavior in subtle but measurable ways. This dressing effect is one of the reasons calculations in quantum field theory are so intricate. Physicists must account for countless virtual processes that contribute small corrections. Individually, these corrections are tiny. Together, they produce results that match experiments to astonishing precision. One famous example of this precision involves the magnetic moment of the electron. Calculations that include virtual particle effects agree with measurements to more than 10 decimal places. This agreement is one of the most successful achievements in the history of science. It is also one of the clearest demonstrations that virtual particles, while not directly observable, are not optional. Leaving them out would break the theory's ability to describe reality. At the same time, it is important not to take the imagery too literally. Virtual particles are not little balls popping in and out of existence in space. They do not have well-defined positions or lifetimes. They are mathematical features of interactions, not independent inhabitants of the vacuum. The language of particles is used because it is familiar and useful. It allows physicists to visualize and calculate complex processes. But the underlying reality is more abstract. It is fields interacting according to quantum rules. In this sense, virtual particles are a bridge between human intuition and mathematical description. They provide a way to talk about something that does not fit neatly into everyday categories. This bridge can be misleading if taken too far. It can tempt people into imagining the vacuum as a frothing sea of particles constantly popping in and out of existence. While this image captures some aspects of vacuum activity, it oversimplifies and distorts others. A more accurate picture is one of continuous fields fluctuating around their lowest energy state. Virtual particles are how those fluctuations appear when we analyze interactions using certain mathematical techniques. They are not the vacuum's contents, they are its language. This distinction matters because it keeps the focus on what is actually being described. The vacuum is not filled with hidden objects. It is structured by rules that allow certain kinds of temporary behavior. Understanding this helps avoid confusion about conservation laws. Virtual particles do not violate conservation of energy or momentum. They obey the rules of the framework in which they appear. Their apparent rule-breaking arises only if we apply classical intuitions where they do not belong. Another subtle aspect of virtual particles is that they do not have to obey the same constraints as real particles. Real particles must satisfy specific relationships between energy, momentum, and mass. Virtual particles do not. This flexibility is what allows them to mediate forces and corrections without being directly observed. This flexibility is not arbitrary. It is constrained by the uncertainty principle and by the structure of the theory. Virtual particles cannot exist for long. They cannot be isolated. They cannot be used to transmit information faster than light. They are confined to the internal workings of interactions. This confinement is crucial. It prevents the vacuum from becoming a source of free energy or paradoxical effects. Virtual particles influence reality without undermining its stability. The vacuum, through these virtual processes, becomes a place of constant negotiation. Fields fluctuate, possibilities are explored, outcomes are shaped, but nothing accumulates uncontrollably. The system remains balanced. This balance is what allows the vacuum to be both active and stable. It is not static, but it is not chaotic either. Its activity is constrained by deep principles that preserve consistency. Virtual particles also play a role in how the vacuum responds to boundaries and conditions. When space is confined or shaped, the allowed virtual processes change. Certain fluctuations are suppressed, others are enhanced. The pattern of virtual activity shifts. This shifting pattern leads to observable effects, such as forces between objects in empty space. These forces are not caused by particles pushing on surfaces. They arise because the vacuum's virtual activity differs inside and outside certain configurations. In this way, virtual particles help translate abstract field behavior into concrete physical consequences. They are the intermediaries that allow the vacuum structure to interact with matter. It is also worth noting that different theories use the concept of virtual particles differently. In some approaches, the language of particles is emphasized. In others, it is downplayed in favor of more abstract field descriptions. The underlying physics is the same, but the storytelling changes. This reminds us that virtual particles are part of a description, not necessarily part of the furniture of the universe. They are tools that help us understand and calculate. They are not things that float around waiting to be found. Still, even as tools, they are remarkably effective. They allow physicists to connect the vacuum's restless behavior to measurable outcomes. They make sense of why empty space influences forces, energies, and interactions. There is a quiet elegance in this. The vacuum does not need to be filled with objects to be influential. Its structure alone is enough. Thinking of virtual particles as passing like daydreams helps maintain this balance. Daydreams are not real in the same way physical objects are, but they are not nothing either. They shape experience. They influence behavior. They pass through awareness without settling. Virtual particles pass through interactions in much the same way. They are never fully present, never fully absent. They exist within the flow of possibility rather than as fixed entities. This perspective also aligns with the broader theme that quantum physics keeps returning to. Reality at its deepest level is not a collection of static things. It is a network of processes, relationships, and probabilities. The vacuum is not empty. It is alive with these processes. Virtual particles are one way of speaking about that aliveness. As attention shifts toward this view, the boundary between something and nothing continues to blur. The vacuum contains no particles, yet it supports endless virtual activity. It does not store objects, but it allows interactions. It is not a container filled with things, but a condition that makes things possible. This idea does not demand that we picture the vacuum as busy or crowded. Its activity is subtle. It does not intrude on everyday experience. It becomes apparent only when we look very closely or when we design experiments sensitive enough to notice its influence. For most of the universe's history, no one noticed these whispers. They were always there, but our tools were not yet refined enough to hear them. As understanding deepened, the vacuum slowly revealed its voice, and even now that voice remains quiet. It does not shout. It does not overwhelm. It murmurs through corrections, through slight shifts, through interactions that pass too quickly to observe directly. Virtual particles are part of that murmur. They pass through the mathematics, through the theory, through our understanding, leaving behind effects that persist even after they are gone. As these ideas drift through the mind, there is no need to pin them down. They are not meant to be held tightly. They are meant to pass, to influence, then to fade. Like daydreams, they do their work without demanding attention. And in doing so, they reveal that even the emptiest places are quietly full of activity, waiting patiently to be noticed. At some point in this journey, a question tends to surface quietly, almost on its own. If the vacuum is supposed to be the lowest energy state of reality, then why does it still seem to carry energy at all? Where does that energy come from? Who allowed it to be there? And perhaps most unsettling of all, why can't we get rid of it? This is where the idea of energy that exists without permission begins to take shape. Not energy stored in fuel or flowing through wires or released in flashes of light, but energy that is simply there by default. Energy that does not need to be added, generated, or supplied. Energy that refuses to vanish, even when everything else is stripped away. In everyday life, energy feels like something that must be earned or transferred. A battery stores it, food provides it, motion carries it, heat spreads it. There is always a source, a cause, a reason you can point to. Energy doesn't just show up uninvited, or so it seems. But quantum physics tells a different story. In the quantum description of reality, energy is not just something systems can have, it is something they cannot entirely avoid. To see why, it helps to return to the idea of a lowest possible energy state. In classical physics, this idea is straightforward. A system rolls downhill until it reaches the bottom. Once there, it stops. No motion, no excess energy. Just rest. Quantum systems do not work this way. They are governed by rules that forbid perfect stillness. The uncertainty principle ensures that certain quantities can never be pinned down exactly at the same time. Among these quantities are energy and time. If a system had exactly zero energy, with no fluctuation whatsoever, that energy would be perfectly defined for all time. That is not allowed. Instead, the system must retain a small amount of residual energy, even in its ground state. This residual energy is called zero-point energy. It is not optional. It is not something added from the outside. It is the minimum energy the system can have while still obeying quantum rules. Every quantum system has zero-point energy, a particle in a box, a vibrating string, an electromagnetic field, and crucially, the vacuum itself. When all particles are removed and all excitations are eliminated, the fields that define reality still remain, and those fields still possess zero-point energy. The vacuum, therefore, is not energy-free. It carries energy simply by existing. This is the energy that exists without permission. It is not granted by a process. It is not borrowed from a source. It is built in. What makes this especially strange is that this energy cannot be accessed in the usual way. You cannot extract zero-point energy from the vacuum and use it to power a device. Countless speculative ideas have tried. None have succeeded. The energy is real, but it is locked into the structure of the vacuum itself. This distinction is subtle but important. The vacuum has energy, but it does not behave like a reservoir you can tap. It influences systems, but it does not offer free work. It shapes reality without becoming a resource. One way to think about this is to imagine a perfectly balanced tension in a stretched surface. The tension is real. It affects how the surface responds to disturbances, but you cannot remove the tension without destroying the surface itself. It is part of what the surface is. Zero-point energy plays a similar role. It defines the baseline behavior of fields. It determines how they fluctuate, how they respond, and how they interact with boundaries and matter. But it cannot be separated from them. What makes this even more unsettling is how large this energy appears to be when calculated. When physicists add up the zero-point energy contributions from all known quantum fields, the result is enormous. far larger than anything we observe directly. This calculation suggests that empty space should be packed with an immense amount of energy. If that energy gravitated in the way energy normally does, the universe would behave very differently. Space would curve violently. Expansion would be extreme. Structures like galaxies would never form, and yet the universe we observe is relatively calm. Space expands, yes, but gently. The energy density associated with empty space, as inferred from cosmological observations, is tiny compared to what theory predicts. This mismatch is one of the deepest problems in modern physics. It is not a small discrepancy. It is off by an absurdly large factor, and it suggests that our understanding of vacuum energy, gravity, or both is incomplete. Despite this uncertainty, one thing is clear. The vacuum's energy is not a mathematical trick. It produces observable effects. One of the most direct manifestations of zero-point energy appears when boundaries are introduced. When space is confined between objects, the allowed vacuum fluctuations change. Some modes are excluded, others remain. The total zero-point energy inside the region differs from that outside. This difference produces measurable forces. The vacuum, through its energy, pushes on matter. The energy involved is tiny, but real. It does not require particles to carry it. It does not require heat or radiation. It emerges purely from the vacuum's baseline energy, adjusting to constraints. This tells us something profound. Energy does not require motion. It does not require particles. It does not even require events. It can exist as a property of a state. This challenges the way energy is usually introduced in basic science education. Energy is often taught as something that moves or changes, but at a deeper level, energy is a measure of a system's configuration, and configurations exist even when nothing appears to be happening. The vacuum's configuration carries energy. That energy influences reality even when no transactions are taking place. This is why calling the vacuum empty is misleading. It lacks matter, but it does not lack structure. It lacks particles, but it does not lack energy. It lacks events, but it does not lack influence. The phrase "without permission" captures something important here. Zero-point energy does not ask whether it is needed. It does not wait for conditions. It does not turn off when inconvenient. It is present because the rules of the universe require it to be. There is no mechanism to remove it entirely. Any attempt to suppress fluctuations in one aspect of a field increases uncertainty elsewhere. The energy shifts, but it does not vanish. This inevitability gives vacuum energy a peculiar status. It is not a choice. It is a consequence. And because it is a consequence of fundamental rules, it appears everywhere, not just in laboratories, not just near particles, everywhere. Deep intergalactic space carries it. The space inside atoms carries it. The space inside you carries it. This does not mean you are filled with exploitable energy. It means that the framework of reality you inhabit has a baseline activity that cannot be erased. This baseline matters even when its effects are small. It sets limits on precision. It shapes stability. It determines how systems behave when cooled to their lowest possible states. In condensed matter physics, zero-point energy explains why certain materials behave differently at very low temperatures. Even when thermal motion is removed, quantum motion remains. Atoms continue to vibrate. Systems refuse to become perfectly still. In particle physics, vacuum energy contributes to the behavior of fields and interactions. It alters masses. It modifies couplings. It affects how forces propagate. In cosmology, vacuum energy appears to be linked to the accelerated expansion of the universe. Space itself seems to carry a small, persistent energy density that pushes galaxies apart over vast distances. This cosmic role of vacuum energy is particularly striking. It suggests that the emptiness between galaxies is not just passive distance. It is an active component of the universe's dynamics. The energy associated with empty space is not diluted as the universe expands. As space grows, more vacuum comes into existence, carrying more energy. The effect does not fade, it accumulates. This behavior is unlike matter or radiation, whose energy densities decrease as space expands. Vacuum energy stays constant per unit volume. It is tied to space itself, not to what moves through it. This is another reason it feels uninvited. It does not obey the usual rules of dilution. It does not thin out. It persists. At the same time, this energy does not dominate in obvious ways. Its influence is subtle, slow, and cumulative. It works over billions of years, not seconds. This slow influence fits with the overall character of the vacuum. It does not rush. It does not overwhelm. It shapes outcomes patiently. There is a temptation to think of vacuum energy as something exotic or unnatural. But in the quantum framework, it is the opposite. It is the most natural thing imaginable. It is what remains when everything else is removed. This reframes the idea of nothingness yet again. Nothing is not a neutral baseline. It is an active condition governed by rules that forbid perfect absence. The vacuum does not need permission to have energy because it is not borrowing energy from anywhere. It is expressing the minimum allowed behavior of the fields that define reality. This realization can feel uncomfortable. It undermines the idea that emptiness is simple. It suggests that even the most stripped-down state of existence carries complexity. But it also offers a kind of quiet coherence. The universe does not rest on fragile stillness. It rests on a structured baseline that remains even when everything else is gone. As attention lingers on this idea, it becomes easier to see how energy, in this deeper sense, is not something added to reality. It is something that reality cannot avoid. At first, the idea sounds almost contradictory. Weight is something we associate with objects, with mass, with substance. A stone has weight, a book has weight. Even air has weight once you think about it carefully. But nothing? Nothing is supposed to be weightless. If something contains no matter, no particles, no substance at all, then surely it cannot weigh anything. And yet, when physics looks closely enough, it finds that even nothing contributes to gravity. Empty space, it turns out, still has weight. To understand why this is not as absurd as it sounds, it helps to loosen the everyday connection between weight and stuff. In daily life, weight feels inseparable from objects. You lift something, your muscles strain, gravity pulls downward. Weight feels like a direct consequence of having mass. But in physics, gravity responds not only to mass, but to energy. Anything that carries energy contributes to gravity, regardless of whether that energy is packaged in particles or hidden in fields. This idea comes from general relativity, where gravity is not treated as a force in the usual sense, but as the curvature of space-time caused by energy and momentum. In this framework, mass is just one form of energy. Motion, pressure, tension, and even the structure of fields all contribute to how space-time bends. Gravity does not ask what something is made of. It responds to how much energy is present and how that energy is distributed. Once this perspective is adopted, the weight of nothing becomes less mysterious. If the vacuum carries energy, and quantum physics tells us that it does, then that energy should gravitate. Empty space should contribute, however subtly, to the curvature of space-time. This is not just a theoretical expectation. It shows up in the equations. When physicists write down the mathematical relationship between space-time curvature and energy, vacuum energy fits naturally into the picture. It enters the equations as a form of energy density associated with empty space itself. What makes this especially strange is how different vacuum energy behaves compared to familiar forms of energy. Matter clumps, radiation spreads out. But vacuum energy remains uniform. It does not dilute as space expands. Each region of space carries the same baseline energy density, simply by being space. This means that empty space has a kind of gravitational influence that does not depend on objects being present. The weight of nothing is not localized in lumps or concentrations. It is spread evenly, everywhere. In everyday terms, this is difficult to visualize. We're used to thinking of gravity as something caused by things. A planet pulls because it is massive. A star bends space-time because it contains enormous amounts of matter and energy. Empty space, by contrast, feels like it should be irrelevant. But general relativity does not privilege matter over emptiness. It treats space-time as responsive to all forms of energy, including those that do not correspond to particles. This leads to a subtle but profound shift in thinking. Weight is no longer a property of objects alone. It becomes a property of states. The vacuum is a state. It is the lowest energy configuration of quantum fields, and that configuration carries energy. Therefore, it contributes to gravity. At first, one might expect this contribution to be negligible. After all, vacuum energy effects are tiny on small scales. They do not cause objects to fall faster. They do not alter everyday gravitational experiences in noticeable ways. But when space itself is considered on cosmic scales, the story changes. Over vast distances and long times, even a small energy density can have significant effects. Observations of the universe's expansion reveal something unexpected. Not only is the universe expanding, but the expansion is accelerating. Galaxies are moving away from each other faster and faster over time. This behavior cannot be explained by matter and radiation alone. The simplest explanation is that empty space itself carries energy with a peculiar gravitational effect. Instead of pulling matter together, this energy causes space to expand more rapidly. In the language of general relativity, vacuum energy produces a kind of negative pressure that affects how space-time evolves. This does not mean that vacuum energy repels matter in the usual sense. It does not push objects away like magnets with opposite poles. Instead, it changes the geometry of space-time in a way that leads to accelerated expansion. Here, the weight of nothing reveals itself not as a downward pull, but as a gentle stretching of space itself. Empty space weighs on the universe, not by collapsing it, but by influencing how it grows. This behavior feels counterintuitive because we associate weight with attraction. But gravity, in general relativity, is not simply attraction. It is geometry. Energy shapes space-time, and space-time tells matter how to move. Vacuum energy shapes space-time in its own way. Its uniform presence leads to a uniform effect. Space expands smoothly, not chaotically. The influence is subtle, steady, and pervasive. What makes this even more unsettling is the magnitude problem. When physicists calculate the expected vacuum energy using quantum field theory, the result is staggeringly large. If that energy gravitated in the straightforward way, space-time would curve enormously. The universe would be unrecognizable. Yet observations show that the gravitational effect of vacuum energy is very small. Not zero, but small. The weight of nothing exists, but it is far lighter than theory naively predicts. This discrepancy suggests that something is missing from our understanding. Perhaps different contributions to vacuum energy cancel out. Perhaps gravity responds differently to vacuum energy than it does to other forms of energy. Or perhaps our theories are incomplete at a fundamental level. Whatever the answer, the problem underscores how real the issue is. This is not a philosophical puzzle about definitions. It is a concrete mismatch between theory and observation that has resisted explanation for decades. Despite this unresolved tension, the basic point remains. The vacuum gravitates. Empty space contributes to the universe's dynamics. Nothing, in a very real sense, still has weight. This idea also shows up in more subtle contexts. In certain systems, changes in vacuum energy can affect gravitational behavior locally. These effects are extremely small and difficult to measure, but they follow naturally from the theory. The fact that gravity responds to energy rather than matter alone means that even changes in field configurations can have gravitational consequences. The vacuum is not exempt from this rule. This blurs the boundary between substance and background. Space is no longer just where gravity happens, it is part of what gravity responds to. In this picture, space-time is not an empty stage with matter acting upon it. It is an active participant, shaped by everything that exists within it, including its own baseline structure. This perspective helps make sense of why the universe behaves the way it does on the larger scales. The expansion of space is not something imposed from outside, it emerges from the properties of space itself. The weight of nothing is not something you could measure with a scale. It does not press down on objects, it does not accumulate in corners, its influence is diffuse and geometric, and yet, without it, the universe would be very different. The long-term evolution of cosmic structure depends on the balance between matter, radiation, and vacuum energy. Remove the vacuum's contribution, and the story changes dramatically. This realization challenges another deeply held intuition. We tend to think that only things that can be pointed to, touched, or isolated can have physical effects. The vacuum defies this. It has no edges, no particles, no texture in the usual sense, and yet it shapes the fate of galaxies. This does not mean that nothingness has suddenly become a thing. The vacuum is not a substance filling space. It does not slosh or flow. Its weight is not due to hidden mass. Instead, its weight arises from the energy inherent in its structure. It is a property of the rules governing fields and space-time, not of material contents. In that sense, the weight of nothing is not an extra feature added to the universe. It is a consequence of consistency. Once energy is allowed to exist in the vacuum, gravity must respond. This consistency is part of what makes modern physics so tightly constrained. You cannot adjust one piece without affecting others. Allow quantum fields to fluctuate and vacuum energy follows. Allow energy to gravitate and vacuum energy must curve space-time. The discomfort arises because the result does not align neatly with intuition. We want emptiness to be neutral. We want nothing to be light, irrelevant, ignorable. Physics does not grant that wish. Instead, it shows that emptiness carries responsibility. It plays a role. It participates. This participation does not mean the vacuum dominates everything. Matter still clumps. Stars still form. Gravity from mass still governs local motion. The weight of nothing is not overwhelming. It is more like a background influence, a steady pressure that becomes noticeable only when viewed over immense scales. This quiet influence fits with the broader character of the vacuum. It does not intrude loudly. It does not disrupt everyday experience. It operates patiently, shaping the universe over billions of years. There is something oddly calming about this. The universe is not driven only by dramatic events and massive objects. It is also guided by gentle, persistent features that act slowly and uniformly. The vacuum does not rush. It does not fluctuate wildly. Its weight is consistent, dependable, and subtle. It reframes the meaning of weight itself. Weight is no longer just about heaviness. It is about influence, about how existence, even minimal existence, affects the structure of reality. Nothing still has weight because nothing is not truly nothing. It is a state with energy, and energy matters. This understanding naturally leads forward. If the vacuum carries weight and energy, and if that energy shapes space-time, then the vacuum is not just a passive backdrop, it is part of the universe's foundation. If everything we've talked about so far feels slightly unsettling, that's because it gently undermines a picture most of us carry without realizing it. The picture where reality is made of solid things, floating in empty space, interacting occasionally and otherwise minding their own business. The deeper physics looks, the harder it becomes to maintain that image. Instead of isolated objects sitting in a void, what emerges is something far more continuous, a background that is not passive, a foundation that is not inert. something closer to a sea than a stage. This is where the idea of a quantum sea beneath reality begins to take shape. The word sea is not meant to suggest waves you could sail on, or currents you could feel pushing against you. It's meant to capture continuity, depth, the sense that what we see on the surface is only part of what's there. In this picture, particles are not the fundamental ingredients of reality. They are surface disturbances, small ripples rising briefly above a much deeper underlying structure. That structure is made of quantum fields. Quantum field theory tells us that every type of particle corresponds to a field that exists everywhere, not just where the particle is detected, everywhere. These fields do not switch on and off. They do not retreat when particles are absent. They are always present, stretching across all of space. When a particle appears, what we are really seeing is a localized excitation of one of these fields, a small region where the field is disturbed in a particular way. When the particle disappears, the field relaxes back toward its lowest energy configuration. But the field itself never goes away. This means that even in a region of space with no particles at all, the fields are still there. They are not perfectly still. They fluctuate. They interact with each other. They carry energy. They define what kinds of disturbances are possible. This is the quantum sea. It is not something added to reality. It is what reality rests on. Particles, forces, and interactions all emerge from it. In classical thinking, emptiness is a default. Things exist against a background of nothing. In quantum thinking, the background is something. Not something you can isolate or point to, but something with structure and rules. The sea is always there, whether or not anything appears on its surface. This perspective changes how we think about existence itself. Objects stop being primary. Processes take their place. An electron, for example, is no longer a tiny bead of matter traveling through space. It is a stable pattern of excitation in an electron field. Its properties, like charge and mass, are not intrinsic labels attached to a point. They arise from how the field behaves. The same is true for every particle. Quarks, photons, neutrinos. All of them are manifestations of underlying fields, different patterns in the same vast ocean. This ocean is not uniform in the sense of being featureless. It has layers. Different fields interact in different ways. Some couple strongly to others, some barely interact at all. The structure is rich, but it is also consistent. What makes this sea quantum is not just that it exists everywhere, but that it obeys quantum rules. It fluctuates. It explores possibilities. It cannot be perfectly still. These fluctuations are not random noise. They are constrained by the mathematical structure of the theory. They follow probabilities that are precisely defined. Over time, they average out in predictable ways. This predictability is why the sea does not overwhelm reality. It supports it. If the quantum sea were chaotic, if its fluctuations accumulated unpredictably, stable structures would be impossible. Atoms would not hold together. Forces would not behave consistently. The universe would be unrecognizable. Instead, the sea is restless but balanced, active but stable, always in motion but never drifting out of control. This balance allows complexity to emerge. It allows particles to exist as long-lived excitations. It allows forces to propagate reliably. It allows matter to clump into stars, planets, and eventually observers who wonder what lies beneath it all. One of the most striking consequences of this picture is that what we call empty space is not a separate category from what we call matter. They are different states of the same underlying fields. Matter is the sea in motion. Vacuum is the sea at rest, as much as quantum rules allow. This continuity blurs the line between existence and non-existence. There is no sharp boundary where something ends and nothing begins. There are only different configurations of the same underlying structure. This helps explain why removing particles does not remove activity. The sea remains. Its surface may calm, but it never becomes perfectly flat. Another way to think about this is to imagine sound in air. When no sound is present, the air molecules are still there. They still move slightly. They still support the possibility of sound. Silence is not the absence of air. It is the absence of a particular pattern of motion. The quantum vacuum is similar. It is not the absence of fields. It is the absence of excitations. The sea remains, ready to support disturbances. This analogy has limits, of course. Air is made of particles. The quantum sea is more fundamental, but the idea that silence is a state of a medium rather than its absence points in the right direction. Once this picture is adopted, many puzzling features of quantum physics begin to feel more natural. Virtual particles, for example, become less mysterious. They are not objects popping in and out of nothingness. They are brief disturbances in the sea, momentary ripples that arise and fade as the fields fluctuate. Vacuum energy also fits more comfortably into this view. A sea under tension has energy even when undisturbed. That energy is not something added. It is inherent in the structure. Even gravity finds a place here. If space-time itself responds to energy, and if the quantum sea carries energy, then the sea must influence space-time. The geometry of the universe is shaped not just by objects floating in space, but by the sea beneath them. This begins to suggest a universe where background and foreground are inseparable. The things we notice are inseparable from the conditions that allow them to exist. It also suggests that reality is not built from discrete pieces assembled in empty space. It is built from continuous fields whose behavior gives rise to discreteness under certain conditions. This is a difficult shift for intuition. Our everyday experience trains us to think in terms of objects, chairs, cups, phones. Even air feels like a thing. Fields feel abstract by comparison. But abstraction here does not mean unreality. Fields are as real as anything physics describes. They just do not align neatly with human-scale perception. The quantum sea is not something you can drain or step into. It is not something you can isolate in a container. It is the container and the contents at the same time. This makes it hard to talk about without slipping into metaphor. Sea, fabric, background, foundation. None of these are exact. They are attempts to gesture towards something that does not have a direct analogue in everyday experience. What matters is not the image, but the relationship. Everything that exists does so within this sea. Nothing exists outside it. Even the concept of outside becomes slippery here. Space itself is part of the structure. The fields fill space because space and fields are intertwined. One does not exist without the other. This interdependence becomes especially clear when considering extreme conditions. In the early universe, for example, the quantum sea may have behaved very differently. Fields may have occupied different configurations. What counted as vacuum then may not count as vacuum now. This suggests that the sea itself can evolve. Its properties can change under certain conditions. The calm surface we experience today may not be the same as the one that existed billions of years ago. If that is true, then the quantum sea is not just beneath reality. It participates in reality's history. This idea is still being explored. Theoretical physics continues to investigate how vacuum states form, how they change, and what role they play in cosmic evolution. Some proposals suggest that phase transitions in the vacuum shaped the forces and particles we observe today. If so, then the sea beneath reality is not just a backdrop, it is an actor. Still, even without these speculative extensions, the basic picture remains powerful. Reality is not a collection of objects in empty space. It is a pattern of excitations in a continuous quantum structure. This structure does not announce itself. It does not demand attention. It simply is. And because it is everywhere, it is easy to overlook. We notice the ripples because they catch our senses. The sea itself remains out of view. But physics has learned to infer its presence by its effects, by how particles behave, by how forces propagate, by how space expands. Each of these observations points back to the same conclusion. There is something beneath the surface. This realization can feel disorienting at first. It dissolves the familiar boundary between something and nothing. It replaces solid ground with a dynamic foundation. But there is also something steady about it. The quantum sea is not fragile. It does not flicker in and out of existence. It persists. It supports. Everything that happens does so within its rules. Every particle, every force, every interaction is a localized expression of its behavior. In that sense, the sea beneath reality is not distant or abstract. It is intimately present in every moment. It is what allows moments to exist at all. As attention rests on this idea, it becomes easier to let go of the need to picture reality as a collection of things. It becomes possible to think of it instead as a continuous process, structured and constrained, but never entirely still. The vacuum is no longer a void. It is the calm surface of a vast quantum ocean. Beneath it, fields fluctuate, energy persists, and possibilities quietly unfold. This does not mean that everything is uncertain or unstable. The sea has rules. It has limits. It has patterns that repeat reliably. Without those patterns, there would be no atoms, no chemistry, no stars, no observers to notice the quiet hum beneath it all. The quantum sea is not a threat to order. It is the source of it. When we talk about forces in everyday life, we usually imagine direct interactions. One object pushes another. A magnet pulls on metal. Gravity draws things downward. These descriptions feel intuitive because they focus on visible causes and visible effects. But as physics has peeled back layer after layer of explanation, that directness has slowly dissolved. What looks like a simple push or pull is, at a deeper level, something far more distributed. Forces do not leap across empty space on their own. They are shaped, carried, filtered, and even softened by the vacuum itself. This is where the vacuum stops being a passive setting and becomes an active shaper of reality. It does not merely allow forces to exist. It influences how strong they are, how far they reach, and how they behave under different conditions. Without the vacuum structure, the forces we take for granted would not look the way they do. Some might not exist at all. To see how this happens, it helps to begin with a shift in perspective. In modern physics, forces are not fundamental actions between objects. They are manifestations of fields. A field is something that exists throughout space and time, assigning a value or structure to every point. The electromagnetic field, for example, exists everywhere, whether or not there are charges nearby. Gravity, in the language of general relativity, is described not as a force but as the geometry of space-time itself. These fields are not laid on top of the vacuum. They are inseparable from it. The vacuum is the state in which these fields are present but unexcited, resting in their lowest energy configurations. When forces act, what we are really seeing are changes in the behavior of these fields against that baseline. The vacuum sets the stage, but it also writes part of the script. Consider the electromagnetic force, one of the most familiar forces in nature. It governs electricity, magnetism, light, chemistry, and much of everyday technology. In quantum field theory, this force arises from the electromagnetic field interacting with charged particles. But that field does not operate in isolation. It exists within the vacuum, and the vacuum responds to it. When a charged particle, such as an electron, exists in space, it does not sit in an inert background. The vacuum around it becomes polarized. Virtual particle-antiparticle pairs briefly appear and influence how the electromagnetic field spreads outward. This effect slightly screens the charge, altering how strongly it interacts at different distances. As a result, the effective strength of the electromagnetic force is not fixed once and for all. It depends on scale. At very short distances, the force behaves slightly differently than it does at larger ones. The vacuum reshapes it. This reshaping is not a correction layered on top of an otherwise complete picture. It is part of what the force is. Without vacuum polarization, the electromagnetic interaction would not match experimental reality. The same idea extends to other forces. The strong nuclear force, which binds quarks together inside protons and neutrons, is also shaped by the vacuum. In this case, the vacuum's behavior is even more dramatic. The strong force is described by a field theory with its own unique structure. The vacuum associated with this field is not empty or simple. It has a complex internal arrangement that affects how quarks behave. One consequence of this structure is confinement. Quarks are never found in isolation. They're always bound together into larger particles. This confinement is not imposed by an external rule. It emerges from how the strong force field interacts with its vacuum. The vacuum resists the separation of quarks, causing the force between them to increase as they are pulled apart. Instead of weakening with distance, as many forces do, it grows stronger. This behavior would be impossible in a featureless vacuum. It depends on the vacuum having a specific structure, one that responds to disturbances in a particular way. In this sense, the vacuum does not merely host the strong force, it enforces its most distinctive property. The weak nuclear force, responsible for certain types of radioactive decay, is shaped by the vacuum in a different way. In this case, the vacuum determines which particles can exist and how heavy they are. Through interactions with the vacuum, certain fields acquire non-zero values even in their lowest energy state. This changes the behavior of other fields that interact with them, giving rise to particle masses. The vacuum here is not just a baseline, it is an active participant in defining what kinds of particles are possible. Without this vacuum structure, many particles would be massless, atoms would not form, chemistry would not exist, the universe would be unrecognizable. Once again, the vacuum is not filling space with a substance, it is providing a condition, a configuration that shapes outcomes. Gravity, though described differently from the other forces, is also shaped by the vacuum. In general relativity, gravity arises from the curvature of space-time caused by energy and momentum. If the vacuum carries energy, then it must contribute to this curvature. This contribution is subtle on small scales, but on cosmic scales it becomes significant. The vacuum influences how space-time expands, how structures form, and how the universe evolves over time. What makes this especially interesting is that the vacuum's influence on gravity does not behave like ordinary matter. Matter clumps. Vacuum energy does not. It remains uniform, creating a smooth effect rather than localized distortions. This uniformity shapes gravity differently. Instead of pulling things together, it alters the expansion of space itself. Here again, the vacuum is shaping a force not by exerting a push or pull, but by modifying the underlying conditions in which motion occurs. This idea of shaping rather than acting directly is key. The vacuum does not throw forces into the universe, it conditions them. It defines their background behavior, their baseline properties, and their response to change. Another way to see this is through how forces propagate. In classical physics, forces can be thought of as instantaneous or mediated by simple signals. In quantum field theory, interactions propagate through fields at finite speeds. Those fields exist within the vacuum, and their behavior depends on the vacuum's properties. The speed of light, for example, is not just a property of photons. It is a property of the electromagnetic field and the vacuum through which it propagates. Change the vacuum's properties, and the behavior of light changes. In certain materials, the vacuum-like environment inside the material modifies how fields propagate. Light slows down, forces behave differently. These effects mirror on a different scale how the true vacuum shapes interactions. This reinforces the idea that the vacuum is not a blank. It has characteristics that influence how fields behave. Even the stability of forces depends on the vacuum. The The fact that forces have consistent strengths across the universe suggests that the vacuum itself is stable. Its configuration does not fluctuate wildly. It maintains its structure over time. If the vacuum were unstable, forces could change unpredictably. Physical laws would not be reliable. Structures could not persist. That reliability is one of the quiet achievements of the vacuum. It holds the rules steady. At the same time, the vacuum is not rigid. Under extreme conditions, it can change. High energies, strong fields, or early universe conditions may have altered the vacuum structure, leading to different force behaviors in the past. This possibility is actively studied in cosmology and high-energy physics. It suggests that what we experience as fixed laws may be contingent on the vacuum's current state. If that is true, then the vacuum is not just shaping forces now. It has shaped them historically. This idea can feel unsettling. It implies that the universe's behavior is not anchored in immutable constants, but in a dynamic underlying state. Yet it also offers an explanation for why the universe looks the way it does. The forces we observe may be the result of the vacuum settling into a particular configuration, a configuration that allows complexity, stability, and long-lived structures. Seen this way, the vacuum is not an obstacle to understanding forces. It is the missing context that makes them intelligible. This context is often invisible because it is so fundamental. We do not notice the vacuum shaping forces in daily life any more than we notice the air shaping sound. It is only when conditions change or measurements become precise that its role becomes apparent. The vacuum's influence is also indirect. It rarely announces itself as a new force. Instead, it appears as corrections, modifications, and constraints. It fine-tunes rather than dominates. This fine-tuning is not a sign of weakness. It is a sign of integration. The vacuum is woven into the behavior of every field. As a result, there is no clean separation between forces and the vacuum. They are different aspects of the same underlying framework. Forces are not things that exist independently and then act through space. They are patterns of field behavior that arise within a structured vacuum. This perspective dissolves the idea of forces as external agents. They become expressions of relationships. It also reframes the vacuum as something more than a lowest energy state. It becomes a medium of consistency, a condition that ensures forces behave coherently across scales. This coherence is essential. Without it, the universe would be fragmented. Local physics would not align with global physics. Predictability would fail. Instead, the vacuum quietly ensures that the same rules apply everywhere, all the time. That quietness is deceptive. The vacuum's role is foundational, but rarely dramatic. It does not shout its influence. It embeds it. This embedding becomes clearer when one considers how deeply forces depend on the vacuum's structure. Change that structure and the forces change. Keep it stable and the forces remain stable. In this way, the vacuum acts as a kind of regulator, not by controlling outcomes directly, but by setting the conditions under which outcomes unfold. As attention lingers on this idea, it becomes harder to think of the vacuum as empty. It is too involved, too consequential. The vacuum shapes forces not as an add-on, but as their environment. It defines what kinds of interactions are possible and how they manifest. And because forces shape everything from atomic bonds to galaxy formation, the vacuum's influence reaches everywhere. This does not mean the vacuum dictates every detail. It provides a framework within which details emerge. That distinction matters. The vacuum is not a scriptwriter controlling every line. It is a grammar that allows coherent stories to be told. With that grammar in place, complexity becomes possible. Without it, there would be only noise. At first, the idea sounds almost playful. Two flat plates placed close together in empty space begin to feel a force between them. No magnets, no electric charge, no air, just emptiness. And yet, the plates move, slowly, gently, but unmistakably. They drift toward one another as if the space between them has decided to intervene. This is where the pressure of emptiness stops being a theoretical curiosity and becomes something you can measure, calculate, and watch unfold. This is where the vacuum presses back. To appreciate why this matters, it helps to remember how counterintuitive the situation really is. In classical thinking, empty space exerts no pressure. Pressure comes from particles colliding with surfaces. Air molecules bounce against walls. Water molecules push outward in all directions. Remove the particles, remove the pressure. A vacuum, by definition, should do nothing at all. And yet, when physicists arranged two uncharged parallel metal plates a tiny distance apart in a vacuum, they found something entirely unexpected. The plates experienced an attractive force, not because something was pushing them together from the outside in a conventional sense, but because the vacuum itself behaved differently inside the narrow gap than it did outside. This effect is subtle. The force is extremely weak unless the plates are placed very close together, separated by distances measured in micrometers or less, but it is real. It has been measured repeatedly with increasing precision, and it does not go away no matter how carefully all other influences are removed. The explanation for this force lies in how the quantum vacuum behaves when it is confined. As we've seen, the vacuum is not empty in the classical sense. It is filled with fluctuating quantum fields. These fields can vibrate in many different ways, producing fluctuations across a wide range of wavelengths. In open space, there are very few restrictions on these fluctuations. The vacuum can explore many possible modes of vibration. But introduce boundaries, and the story changes. When two conducting plates are placed close together, they impose constraints on the quantum fields between them. Certain fluctuations are no longer allowed in the gap. Only waves of specific wavelengths can exist there. Outside the plates, where there is no such confinement, a broader range of fluctuations remains possible. This difference matters. Each allowed fluctuation contributes a tiny amount of energy. When some fluctuations are excluded from the space between the plates, the total vacuum energy in that region is reduced compared to the surrounding space. Nature, it turns out, is sensitive to differences in energy, even when those differences arise from nothing more than constraints on emptiness. The result is a pressure imbalance. The vacuum outside the plates has slightly more energy than the vacuum inside. That energy difference manifests as a force pushing the plates inward. The plates are not pulled together by an object. They are pushed together by the vacuum's unequal behavior. This is what makes the effect so striking. It is not caused by something added. It is caused by something removed. The vacuum does not behave the same everywhere once boundaries are introduced. It responds to geometry. It cares about shape, distance, and constraint. It is not indifferent to its environment. What's remarkable is that this force can be calculated precisely using quantum field theory. The predicted strength depends on the distance between the plates and fundamental constants of nature. When experiments measure the force, the results match the predictions. Not approximately, but closely. This agreement tells us something important. The vacuum's fluctuations are not vague philosophical ideas. They are concrete features of reality that produce measurable outcomes. The pressure of emptiness is not metaphorical, it is literal. It's worth pausing to appreciate how strange this is. Two objects, placed in nothing, experience a force because nothing is behaving differently in different places. No particles are exchanged. No classical fields are involved. The vacuum itself supplies the pressure. In everyday terms, this would be like placing two walls in silence and finding that the silence pushes them together. Of course, the silence analogy breaks down quickly, but the sense of quiet intervention remains. The vacuum does not announce itself loudly. It applies pressure gently, persistently, as a consequence of its structure. This pressure is not universal in direction. Under different geometries, the vacuum can behave differently. Certain configurations can lead to repulsive effects. The details depend on how boundaries constrain fluctuations. This sensitivity to geometry highlights something profound. The vacuum is not just a background condition. It is a system with degrees of freedom that respond to constraints. In classical physics, boundaries only matter when something inside interacts with them. In quantum physics, boundaries matter even when nothing is inside. This has far-reaching implications. It means that empty space has properties that can be engineered. By shaping boundaries at very small scales, it is possible to influence vacuum behavior. This idea has inspired research into micro and nanoscale devices where vacuum forces can become significant. At extremely small distances, the pressure of emptiness is no longer negligible. It can influence how tiny components move and interact. But beyond applications, the Casimir effect serves as a conceptual anchor. It grounds the abstract idea of vacuum fluctuations in something tangible. It shows that empty space does not merely influence calculations, it moves matter. This is one of the reasons the effect is often highlighted in discussions of the quantum vacuum. It takes something deeply theoretical and makes it physical. The plates do not care about interpretation. They move. Another important aspect of this effect is what it does not allow. Despite the vacuum exerting pressure, it does not offer free energy. You cannot arrange plates in a cycle and extract unlimited work from the vacuum. The forces are conservative. Any work done by the vacuum must be paid back when configurations are reversed. This preserves consistency with thermodynamics. The vacuum influences systems, but it does not violate fundamental limits. It shapes behavior without becoming an energy source in the usual sense. This balance is characteristic of vacuum phenomena. They are powerful enough to matter but constrained enough to avoid paradox. The pressure of emptiness also reinforces a recurring theme. The vacuum is not an absence, it is a state with structure. That structure includes allowable modes, energy levels, and responses to constraint. When space is unconstrained, the vacuum settles into a particular pattern of fluctuations. When space is confined, that pattern changes. The vacuum adapts. This adaptability is not arbitrary. It follows precise mathematical rules. The fluctuations that remain are those compatible with the boundary conditions imposed. In that sense, the vacuum behaves like a responsive system. It is sensitive to context. This sensitivity raises deeper questions. If the vacuum responds to boundaries on small scales, does it respond to boundaries on cosmic scales? Does the shape and size of the universe influence vacuum behavior? Does the expansion of space alter the vacuum structure? These questions are not idle speculation. They are active areas of research. Cosmology and quantum field theory continue to explore how large-scale structure and vacuum energy interact. The Casimir effect provides a small-scale analogue of these questions. It shows that vacuum energy depends on geometry. On cosmic scales, geometry changes over time. This connection hints that the vacuum may play a role not just in local interactions, but in the evolution of the universe itself. At the same time, it's important not to overextend the analogy. The forces involved in laboratory Casimir experiments are tiny. They do not dominate everyday physics. Their importance is conceptual rather than practical. They show us that our assumptions about emptiness are incomplete. There is also something quietly elegant about how the effect arises. Nothing dramatic happens. No new particles appear. No bursts of radiation occur. The vacuum simply adjusts its internal bookkeeping, and the plates respond. This quietness fits the overall character of vacuum phenomena. They rarely announce themselves with spectacle. They prefer to reveal themselves through careful measurement. The pressure of emptiness is a whisper, not a shout. And yet, once heard, it cannot be unheard. It permanently alters how emptiness is understood. After learning about this effect, it becomes difficult to think of empty space as neutral. It has preferences, it responds to constraints, it exerts influence. This influence does not mean the vacuum is a substance filling space. It does not mean space is thick or resistant. The pressure arises from differences in allowed quantum behavior, not from material collisions. That distinction matters. The vacuum remains non-material, even as it produces material effects. This duality is part of what makes quantum physics so challenging and so compelling. The most important features of reality may not align with everyday categories. The Casimir effect sits at this boundary. It is physical enough to measure, but abstract enough to resist simple explanation. It teaches us that forces can arise not only from things interacting, but from constraints shaping possibilities. The vacuum pushes because it cannot behave the same way everywhere at once when boundaries are present. This idea extends beyond plates. Any situation that restricts the allowed states of quantum fields can, in principle, lead to vacuum forces. In this sense, the pressure of emptiness is not a special case. It is a general feature of how quantum fields respond to structure. What makes the plate experiment special is its simplicity. Two objects. Empty space. A measurable force. It strips the situation down to its essentials. As this understanding settles, the vacuum becomes harder and harder to ignore. It is not content to remain a background concept. It insists on participating. This participation does not feel intrusive. It feels inevitable. Once the rules of quantum physics are accepted, the behavior follows. The vacuum presses because it must, and this pressing is not limited to metal plates in laboratories. It is part of a broader pattern in which the vacuum structure influences everything built upon it. For a long time, it was comforting to think of the universe as a kind of theatre. Space was the stage, matter and energy were the actors. Events unfolded against a fixed backdrop that did not interfere, did not react, and did not care what story was being told upon it. This image was simple, intuitive, and deeply persuasive. Even as physics advanced, that quiet stage remained in the background, unchanged and unquestioned. But as the idea of the quantum vacuum has slowly taken shape, that image has begun to soften and blur. The stage, it turns out, is not empty. It is not passive, and it is very much part of the performance. When physicists speak of the vacuum as a cosmic stage, they no longer mean a neutral platform on which the universe plays out. They mean something closer to a living framework, a condition that determines what kinds of actors can exist, how they move, and what kinds of stories are even possible. The vacuum does not merely host the universe, it helps write its rules. To see how this shift happened, it helps to look at how the idea of a stage evolved in physics. In classical mechanics, space and time were absolute. They existed independently of matter. Events happened within them, but space and time themselves were unaffected. You could remove all objects from the universe, and space and time would still be there, ticking along and stretching out endlessly. This view fit neatly with everyday experience. Rooms remain even when empty. Time passes whether or not anything interesting happens. The universe seemed to work the same way. But this picture began to fracture with the arrival of relativity. Space and time were no longer separate, fixed entities. They merged into space-time, a unified structure that responds to energy and momentum. Massive objects bend it. Motion affects it. Time flows differently depending on gravity and speed. The stage, in this new picture, was no longer rigid. It could warp and curve, it could stretch and compress. Still, even in this more flexible form, space-time was often treated as a geometric arena. Matter told space-time how to curve, and space-time told matter how to move, but the vacuum itself was still often imagined as an empty version of that arena. Quantum physics complicated this further. It revealed that even when matter is absent, fields remain. And those fields are not silent. They fluctuate. They carry energy. They influence what happens when matter appears. This is where the idea of the vacuum as a cosmic stage takes on a deeper meaning. The vacuum is not just empty space-time. It is space-time filled with quantum fields in their lowest energy states. It is a condition rich with structure, potential, and constraint. In this sense, the vacuum does not simply provide a place for the universe to exist. It provides the conditions that make existence possible. Consider particles once again. In the older stage and actor picture, particles were things that entered the stage, interacted, and left. In the quantum picture, particles are excitations of fields that already exist everywhere. They are not guests arriving on stage, they are ripples in the stage itself. This changes the role of the vacuum profoundly. The vacuum is not waiting for particles to show up. It already contains the fields from which particles emerge. The actors are not separate from the stage, they are patterns within it. This is not just a philosophical reinterpretation, it has measurable consequences. The properties of particles depend on the vacuum structure. Their masses, charges, and interaction strengths are shaped by how fields behave in the vacuum. If the vacuum were different, the particles would be different. Some might not exist at all. This dependence means that the vacuum sets the casting rules for the universe. It determines which roles are available and which are forbidden. The same is true for forces. As we've seen, forces arise from fields interacting within the vacuum. The vacuum shapes how those fields propagate, how they interact, and how strong they appear at different scales. This makes the vacuum a kind of regulatory framework. It does not dictate specific outcomes, but it constrains possibilities. It defines what kinds of interactions can occur and how they behave. In theatre terms, the vacuum is not just the stage floor. It is the lighting, the acoustics, the layout of entrances and exits. It shapes how the performance unfolds even when it remains unnoticed. This becomes especially clear when we look at the universe on its larger scales. Cosmology, the study of the universe as a whole, is deeply entangled with the behavior of the vacuum. Observations show that the universe is expanding and that this expansion is accelerating. The simplest explanation involves energy associated with empty space itself. The vacuum appears to exert a gentle but persistent influence on the geometry of space-time. This influence is uniform. It does not clump. It does not form structures. It acts everywhere equally. This uniformity is precisely what one would expect if the vacuum itself were contributing. Here, the vacuum is not just shaping local interactions, it is shaping the global evolution of the universe. This elevates the vacuum from background condition to cosmic participant. It becomes part of the universe's story, not just its setting. What makes this especially striking is how quiet this participation is. The vacuum does not explode or collapse. It does not produce dramatic local effects. Its influence is slow, steady, and cumulative. Over billions of years, that gentle influence becomes decisive. This reinforces a theme that has appeared again and again. The vacuum does not announce itself loudly. It works in the background, shaping outcomes through consistency rather than spectacle. In this way, the vacuum resembles the most effective stage designs. They do not draw attention to themselves. They simply make certain kinds of performances possible. Another aspect of the vacuum as a cosmic stage is its apparent stability. Despite its fluctuations, despite its energy, the vacuum remains remarkably consistent across vast stretches of space and time. The laws of physics appear the same in distant galaxies as they do here. Forces behave the same. Particles have the same properties. This uniformity suggests that the vacuum structure is stable. If the vacuum were unstable, if it changed unpredictably, the universe would not be coherent. Physical laws would vary from place to place. Structures would not persist. The fact that the universe is orderly is, in part, a testament to the vacuum's reliability. At the same time, there are hints that the vacuum may not be entirely immutable. The early universe appears to have gone through phases where the vacuum structure was different. Fields may have settled into new configurations as the universe cooled and expanded. These changes could have altered particle properties, force strengths, and interaction patterns. In other words, the stage itself may have been rearranged between acts. If this is correct, then the vacuum has a history. It has evolved. Its current form may be the result of earlier transitions. This idea opens up fascinating possibilities. It suggests that the universe we observe is not the only possible one. Different vacuum configurations could, in principle, give rise to very different physics. In this sense, the vacuum is not just a stage, but a choice among many possible stages. Why this particular one exists with its particular properties remains an open question. Some theories suggest that many vacuum configurations may exist, each giving rise to different physical laws. Others seek a deeper principle that uniquely selects this one. Regardless of how that question is answered, the role of the vacuum remains central. It is the framework within which everything else unfolds. This framework is subtle. It does not impose obvious constraints. It allows complexity, diversity, and change, but it also enforces consistency. It is this balance that makes the vacuum such a compelling concept. It is permissive without being chaotic, structured without being rigid. The vacuum as a cosmic stage also reframes the meaning of emptiness. Empty regions of space are not empty in the sense of being irrelevant. They are full of the same fields, the same structure, the same conditions that operate everywhere else. The difference between a crowded region of space and an empty one is not the presence or absence of the stage. It is the presence or absence of excitations upon it. This continuity means that the vacuum connects everything. There are no gaps in reality where the rules stop applying. The stage does not end at the edges of matter. This helps explain why interactions can occur across vast distances. Fields extend everywhere. The vacuum provides continuity. It also explains why isolating a system completely is so difficult. Even in extreme vacuums, fields remain. The system is never truly cut off from the underlying structure. In this sense, the vacuum is the ultimate environment. Everything exists within it, whether noticed or not. This idea has a quiet philosophical resonance. It suggests that existence is not something that happens against a backdrop of nothingness. It happens within a structured context that is always present. Nothing exists in isolation, not even emptiness. The vacuum does not impose meaning or direction. It does not choose outcomes. It provides conditions. Those conditions are enough to allow the universe to unfold with remarkable richness. As this picture settles, it becomes easier to let go of the image of the vacuum as a void. It becomes more natural to think of it as a foundation. Not solid, not material, but essential. The cosmic stage is not empty boards and curtains. It is a framework of fields, energies, and constraints that make performance possible. And like any good stage, it is rarely noticed when it is working well. The audience focuses on the actors, the dialogue, the drama. The stage fades into the background. Physics, in its slow and careful way, has learned to look behind the scenes, and what it has found is not emptiness but structure. Not silence, but a quiet hum of rules being followed. The vacuum as a cosmic stage is not a poetic flourish. It is a literal description of how deeply the vacuum is woven into reality. Every force, every particle, every interaction unfolds within its conditions. It does not demand attention. It does not seek recognition. It simply remains, steady and patient, holding the universe together while allowing it to change. As this understanding deepens, the vacuum becomes less mysterious and more familiar. Not because it becomes simple, but because its role becomes clear. It is not nothing. It is not something in the usual sense. It is the condition that makes something possible. And with that condition quietly in place, the universe continues its long, unhurried performance, resting always upon a stage that is anything but empty. Long before the phrase dark energy entered the scientific vocabulary, astronomers already knew that the universe was expanding. Galaxies were moving away from one another, their light stretched toward redder wavelengths as space itself grew larger. This discovery alone was strange enough. It meant the universe was not static, not fixed, not eternal in the way many had imagined. Space was changing. It was stretching. But for a while, there was a comforting assumption attached to this idea. The expansion was expected to slow down. Gravity, after all, pulls things together. Over time, the mutual attraction of all the matter in the universe should gradually decelerate the expansion, like a ball thrown upward, eventually losing momentum. That expectation felt reasonable. It matched intuition. It aligned with how forces usually behave, and for decades it went largely unquestioned. Then the measurements became precise enough to test it. When astronomers began observing very distant stellar explosions, using them as markers to trace the universe's expansion history, they found something deeply unexpected. The expansion was not slowing down, it was speeding up. Galaxies were not just drifting apart, they were accelerating away from one another, as if space itself were being gently but persistently urged outward. This discovery did not arrive with fanfare or spectacle. It arrived as a quiet discrepancy in data, a mismatch between what was expected and what was measured, but its implications were enormous. Something was pushing the universe apart, and whatever it was not behaving like matter or radiation. This is where dark energy enters the story. The name itself can be misleading. Dark energy is not dark because it absorbs light, nor because it hides in shadows. It is dark because we do not know what it is. The term is a placeholder, a label for an effect we observe but do not yet fully understand. What we do know is how it behaves. Dark energy appears to be uniform. It does not clump into structures. It does not collect in galaxies or stars. It does not dilute as the universe expands. Its density remains roughly constant per unit volume of space. This last feature is especially important. Matter spreads out as space expands. Radiation does too. Their influence weakens over time. Dark energy does not. As more space comes into existence, more dark energy comes with it. This behavior makes dark energy closely resemble vacuum energy, the energy associated with empty space itself. In fact, the simplest explanation for dark energy is that it is vacuum energy. If the quantum vacuum carries energy, and if that energy gravitates, then empty space should influence the expansion of the universe. And because vacuum energy is tied to space itself, rather than to particles within space, its influence would grow as the universe expands. This is exactly what observations suggest. The stretching of space appears to be driven not by matter pushing outward, but by the properties of space itself. The vacuum is not just along for the ride, it is contributing to the motion. To see why this leads to accelerated expansion, it helps to revisit how gravity works in general relativity. Gravity is not simply attraction, it is the response of space-time to energy and pressure. Both matter and pressure contribute to how space-time curves and evolves. Vacuum energy has a peculiar kind of pressure. Instead of resisting expansion, it promotes it. This does not mean it pushes in the usual sense. It means that when its energy density is plugged into the equations that govern space-time, the result is accelerated expansion. This outcome feels counterintuitive because we tend to associate energy with pulling things together. But the equations do not care about intuition. They care about signs, relationships, and balances. Vacuum energy enters those equations in a way that leads to repulsive gravitational effects on large scales. Space stretches faster and faster, not because something is being flung outward, but because the geometry of space-time is evolving under the influence of the vacuum. This stretching is smooth. It does not tear objects apart locally. Galaxies remain intact. Solar systems remain bound. At small scales, gravity and other forces dominate. The expansion becomes noticeable only across vast distances. This scale dependence is why the effect remained hidden for so long. It is not something you can observe by watching nearby objects drift apart. It reveals itself only when looking across billions of light years and billions of years. The vacuum's influence is patient. What makes this especially striking is that the stretching of space is not slowing down as matter becomes more dilute. It is becoming more dominant. As the universe expands, matter thins out. Dark energy does not. Over time, it comes to dominate the universe's dynamics. This means that the future of the universe is likely to be shaped increasingly by the vacuum. Galaxies will continue to move farther apart. Regions of space will become increasingly isolated. Over extreme extremely long timescales, distant galaxies may fade beyond observable reach, not because they disappear, but because space between us and them stretches too quickly for light to bridge the gap. All of this arises from the properties of empty space. This realization deepens the role of the vacuum even further. It is not just shaping local forces or microscopic interactions, it is shaping the destiny of the cosmos. At the same time, it raises uncomfortable questions. When physicists calculate the expected vacuum energy using quantum field theory, the result is vastly larger than what is observed as dark energy. The predicted value is so enormous that, if correct, the universe would have expanded violently from the beginning, preventing the formation of galaxies, stars, and life. Instead, the observed vacuum energy is small, but not zero. This mismatch is one of the greatest unsolved problems in theoretical physics. It suggests that something is missing from our understanding of how vacuum energy contributes to gravity. Some possibilities involve cancellations. Perhaps different contributions to vacuum energy nearly cancel each other out, leaving a small remainder. Others suggest that gravity responds differently to vacuum energy than to other forms of energy. Still others propose that what we call vacuum energy is not constant but slowly evolving. Each of these ideas is being explored. None has yet provided a definitive answer. What matters for our story is not the solution, but the implication. The vacuum is not a negligible detail. Its properties matter on the largest scales imaginable. The stretching of space is not driven by distant objects pulling on each other. It is driven by the baseline condition of space itself. This shifts the mental picture of cosmic expansion. Instead of imagining galaxies flying apart through static space, it becomes more accurate to imagine space itself swelling, carrying galaxies along with it. The vacuum is not being stretched like a rubber sheet under tension. It is the thing that is stretching. This distinction is subtle, but important. It reinforces the idea that space is not a container separate from what happens within it. It is part of the system. When space stretches, the vacuum stretches. When the vacuum stretches, its energy contributes to further stretching. This feedback is gentle, not explosive. It unfolds over immense timescales, but it is relentless. There is something quietly unsettling about this. The emptiness between galaxies is not inert. It is active in shaping the universe's future. It does not require matter to exert influence. It acts simply by being there. This behavior also highlights how different vacuum energy is from anything we encounter in daily life. It does not behave like a gas filling space. It does not thin out when space expands. It does not cluster or flow. It behaves like a property of space itself. This is why dark energy is often described as a property of the vacuum rather than a substance within it. The term energy here can also be misleading. It suggests something dynamic, something that does work. Vacuum energy is subtler. It influences geometry rather than motion. It alters the rules rather than pushing objects directly. In that sense, the stretching of space is not caused by a force in the traditional sense. It is caused by the vacuum's contribution to space-time structure. This again emphasizes how the vacuum functions as a cosmic stage. It does not merely host events. It shapes the environment in which events unfold, even on the larger scales. Another striking aspect of dark energy is its apparent uniformity. No matter where astronomers look, the expansion behaves the same. There are no regions where dark energy is stronger or weaker. It appears evenly distributed across the observable universe. This uniformity suggests that dark energy is tied to the vacuum in a deep way. It is not associated with particular objects or regions. It is associated with space itself. This also means that dark energy does not produce local gradients. There is no direction to its influence. It does not pull or push objects relative to one another. It simply changes how space evolves. Because of this, dark energy is extremely difficult to detect directly. It does not produce signals in detectors. It does not interact with particles in obvious ways. Its presence is inferred from geometry and motion on cosmic scales. This indirectness fits the overall pattern of vacuum phenomena. The vacuum rarely announces itself. It reveals its presence through careful observation and long-term effects. The stretching of space is one of the clearest such effects. It also reinforces the idea that emptiness is not a void. It has structure. It has influence. It participates. As the universe continues to expand, the role of dark energy will become increasingly dominant. Matter will become more isolated. Structures will form less frequently. The universe will grow quieter, not because activity ceases, but because regions lose contact. This future is shaped not by explosions or collisions, but by the quiet persistence of the vacuum. There is something fitting about that. The same vacuum that whispers at the smallest scales also guides the universe at the largest. This dual role underscores how deeply the vacuum is woven into reality. It is not just beneath particles or between forces, it is beneath space-time itself. And yet, despite its importance, the vacuum remains elusive. We can measure its effects, but we do not yet understand its origin. We can describe its influence, but we cannot yet explain why it has the value it does. This gap in understanding is not a failure. It is an invitation. It suggests that the vacuum may be pointing toward deeper principles not yet discovered, that the stretching of space may be a clue, not just a consequence. As attention rests on this idea, it becomes easier to see why the vacuum keeps returning as a central character in modern physics. It connects the smallest fluctuations to the largest motions. It links quantum rules to cosmic destiny. The stretching of space is not an accident layered on top of the universe. It is an expression of the vacuum's nature, and that nature remains one of the most profound open questions in science. For now, it is enough to recognize the pattern. Empty space carries energy. That energy shapes space-time. Space-time stretches. And the universe evolves accordingly. Nothing pushes, nothing pulls, and yet everything moves. The vacuum does not rush. It does not shout. It stretches space patiently, steadily, shaping the long arc of cosmic history as quietly as it shapes the tiniest quantum fluctuation. At a certain point, after following the vacuum from the smallest fluctuations to the stretching of the entire universe, a question begins to feel unavoidable. If empty space carries energy, shapes forces, presses on objects, and drives cosmic expansion, then what exactly is the universe resting on? If the vacuum itself is active, structured, and influential, is there anything beneath it? Or is everything, in some profound sense, balanced on nothing at all? This question is not a rhetorical flourish. It sits quietly at the edge of modern physics, where intuition thins out and familiar categories stop being reliable. It does not ask whether the universe has meaning or purpose. It asks something more technical, but no less unsettling. Is there a deeper foundation beneath the vacuum, or is the vacuum the foundation? And if it is, what does that mean for stability, for existence, and for the long-term fate of everything? To begin approaching this, it helps to clarify what balance means in this context. Balance does not mean that the universe is delicately perched, ready to tip into collapse at the slightest disturbance. It means something subtler. It refers to whether the structures we observe depend on a deeper layer of support, or whether they emerge from conditions that have no underlying substance at all. In everyday experience, balance usually implies support. A table rests on a floor. A building rests on a foundation. Remove the support and the structure falls. This way of thinking is so ingrained that it's hard to imagine anything existing without something underneath it. Physics, however, has been steadily dismantling this assumption. In classical mechanics, space and time were taken as givens. They did not need explanation. They existed. Full stop. Matter moved within them, but space and time themselves were not the things that needed support. They were the backdrop. Relativity complicated this picture by showing that space-time is dynamic. It can bend, stretch, and evolve. But even then, space-time itself was often treated as fundamental. It did not sit on anything else. It simply was. Quantum physics then added another layer. It showed that what we call empty space is not empty, but filled with fields and fluctuations. The vacuum became a state rather than an absence. Now the question sharpens. If the vacuum is a state of fields, what are those fields sitting in? If space-time is dynamic and influenced by energy, what is space-time itself made of? Is there a deeper substrate beneath the vacuum, or is the vacuum as deep as it goes? Some approaches to physics suggest that the vacuum is not the bottom layer. They propose more fundamental structures beneath it. Others suggest that asking for a deeper layer may be a mistake, a projection of everyday intuition onto a domain where it no longer applies. To see why this question is so difficult, consider how the vacuum is defined. In quantum field theory, the vacuum is the lowest energy state of all fields. It is not defined by what it contains, but by what it cannot give up. It is the state that remains when all possible excitations are removed. This definition is relational. It does not say what the vacuum is made of, it says how it behaves relative to other states. That alone should give pause. If the vacuum is defined by a relationship rather than a substance, then looking for something beneath it may be like looking for what lies north of the North Pole. The question may not be well posed, and yet the discomfort remains. The vacuum carries energy. It influences gravity. It shapes space-time. These are substantial effects. How can something that is not made of anything have such influence? One response is to accept that fields themselves are fundamental. There is nothing beneath them. They do not sit on a medium. They are the medium. Space, time, matter, and energy are all manifestations of field behavior. In this view, the universe is not balanced on nothing. It is balanced on rules, on mathematical relationships, on constraints that define how fields behave. There is no deeper substance because substance is not the right category at this level. This answer is internally consistent, but it can feel unsatisfying. It replaces a physical foundation with an abstract one. Instead of a floor, we get equations. Another response goes further and suggests that even fields may not be fundamental. Some theories propose that space-time itself is emergent, that it arises from more basic, non-spatial structures, such as networks of relationships, quantum information, or discrete events. In these approaches, space and time are not primary ingredients. They are effective descriptions that emerge at large scales, much like temperature emerges from the motion of molecules. If space-time is emergent, then the vacuum, which is defined within space-time, would also be emergent. It would not be the bottom layer. It would be a surface phenomenon arising from deeper processes. In that case, the universe might indeed be balanced on something else, but that something would not look like space, matter, or energy as we understand them. It would be more abstract, more relational, and less intuitive. Still, other perspectives suggest that the universe may be self-supporting. That is, it does not rest on anything external. Its structure is internally consistent. The vacuum exists because the rules that define it exist, and those rules do not require an external foundation. This idea can be difficult to accept because it violates a deeply ingrained expectation. We want explanations to bottom out in something solid. But physics has repeatedly shown that solidity is often an illusion. Atoms are mostly empty space. Particles are excitations of fields. Fields are defined by equations, and equations describe relationships, not substances. At each step, the apparent foundation dissolves into something less tangible. This pattern suggests that the question of what the universe is balanced on may not have an answer in the way we expect. There may be no ultimate thing beneath it all. Instead, there may be a network of consistent relationships that do not require external support. This is where the idea of balance becomes metaphorical rather than mechanical. The universe is not balanced the way a chair is balanced on legs. It is balanced the way an equation is balanced, through internal consistency. The vacuum in this picture is not a platform, it is a condition that satisfies certain rules. Those rules are not enforced by a deeper layer, they are simply the way reality behaves. This does not mean the vacuum is fragile. On the contrary, it is remarkably stable. Despite fluctuations, despite energy, despite its influence on space-time, the vacuum persists. It does not collapse. It does not unravel. Its stability suggests that whatever underlies it, whether that is nothing at all or something we do not yet understand, is sufficient. The phrase, balanced on nothing, can be misleading here. It implies precariousness. But the universe does not appear precarious. It appears robust. The vacuum's energy does not fluctuate wildly. Forces remain consistent. Particles retain their properties. Space-time behaves predictably over vast scales. This robustness argues against the idea that the universe is teetering on the edge of collapse due to a lack of foundation. Instead, it suggests that the vacuum, whatever its ultimate nature, provides a stable baseline. Still, the question can be reframed, not as what is the universe balanced on, but as what prevents the universe from falling apart. In classical systems, stability often comes from potential wells, from energy minima. Systems settle into configurations that resist change. The vacuum is such a configuration. It is the lowest energy state of the fields. This means that the vacuum is stable by definition. Any deviation from it requires energy. Left alone, systems tend to relax back toward it. In that sense, the vacuum is not something that needs support. It is the support. It is the state toward which everything gravitates when disturbances fade. This is a powerful idea. It suggests that stability does not come from beneath, but from within. The universe is stable because its rules favour stable configurations. This internal stability may be the deepest kind of balance. However, this does not resolve all questions. The vacuum we observe may not be the absolute lowest possible state. Some theories suggest that it could be metastable, that is, stable for extremely long times, but not forever. If that were the case, the universe could, in principle, transition to a different vacuum state with different properties. Such a transition would be catastrophic on cosmic scales, altering forces, particles, and space-time itself. This possibility is speculative, but it underscores the idea that the vacuum stability is an active subject of study. Balance here is not guaranteed by an external anchor. It is maintained by the vacuum's position in the landscape of possible states. This landscape idea introduces another layer. Instead of a single vacuum, there may be many possible vacuum states, each corresponding to different physical laws. The universe we observe occupies one such state. Why this one? That question remains open. Some propose that many vacuum states exist, each realized in different regions or universes. Others seek a principle that uniquely selects the vacuum we inhabit. Regardless of which approach turns out to be correct, the implication is similar. The vacuum is not resting on a deeper physical flaw. It is a state among states, defined by its properties and relationships. This brings us back to the original question. Is the universe balanced on nothing at all? In a literal sense, yes. There is no physical substance beneath the vacuum holding it up. There is no cosmic shelf. In a deeper sense, no. The universe is balanced on structure, on rules, on consistency, on relationships that do not require material support. This answer may feel unsatisfying if one expects a tangible foundation, but it aligns with the direction physics has been moving for over a century, away from substance towards structure. It also aligns with the idea that emptiness is not the absence of order. It is a particular kind of order. The vacuum is not chaos. It is highly constrained. Its fluctuations follow rules. Its energy has specific properties. Its influence on space-time is predictable. This order is what allows the universe to exist without an underlying material base. From this perspective, the phrase, nothing at all, becomes misleading. The vacuum is not nothing. It is the most minimal something allowed by the rules. It contains no particles, but it contains structure. It contains no objects, but it contains relationships. It contains no events, but it contains the conditions under which events can occur. So the universe is not balanced on nothing in the everyday sense. It is balanced on the quiet, persistent presence of the vacuum, and the vacuum in turn is balanced on the rules that define it. Those rules may be fundamental, or they may emerge from something deeper. That remains an open question. But either way, the vacuum does not appear to be precarious. It does not wobble. It does not strain under the weight of the universe. It supports everything simply by being the lowest energy configuration available. This idea carries a certain calm. The universe is not hanging over an abyss. It is resting in a state of minimal tension. That does not mean change is impossible. It means change requires energy. Disturbances rise and fall against a stable background. As these thoughts settle, the image of balance shifts. It becomes less about support and more about equilibrium. The universe is balanced not because something holds it up, but because its rules allow it to settle. That is a different kind of security than the one we are used to, but it is no less real, and it leads naturally to the next question. If the vacuum is a state among possible states, if it is stable, but perhaps not eternal, what would happen if it changed? What would it mean for the universe if the foundation itself shifted? There is a moment when following the vacuum far enough where its role quietly crosses a threshold. It stops being just a background condition or even a cosmic influence and becomes something more consequential. Not because it suddenly acts or intervenes, but because the entire future of the universe appears to depend on which vacuum state exists and whether that state remains unchanged. At that point, it becomes reasonable to say that the vacuum does not merely shape reality. It may decide the fate of everything. This idea does not come from dramatic speculation. It emerges from careful, almost cautious reasoning within modern physics. The vacuum, as it is understood today, is not guaranteed to be unique, nor is it guaranteed to be eternal. It is defined as a lowest energy state, but that lowest state may only be local rather than absolute, and if that is true, then the universe could, in principle, change its most basic conditions. To see why this matters, it helps to revisit how stability works in physical systems. A system is stable if small disturbances do not cause it to change its overall state. A ball resting at the bottom of a valley is stable. Push it slightly and it rolls back. But if the ball is resting in a shallow dip on the side of a much deeper valley, the situation is different. It may appear stable for a long time, but a sufficiently large disturbance could send it rolling into a completely different configuration. This distinction between absolute stability and metastability is subtle, but crucial. When physicists talk about the vacuum, they often mean the lowest energy state available under current conditions. But that state may not be the lowest possible state in an absolute sense. There may exist other vacuum states with lower energy, separated by barriers that are difficult to cross. If the universe is currently in such a metastable vacuum, then it is stable against small fluctuations but not absolutely immune to change. This is not an exotic idea. Metastability appears throughout physics. Supercooled liquids, radioactive nuclei, and many chemical systems exist in states that persist for long periods, but are not truly permanent. What makes the vacuum different is the scale of the consequences. A change in vacuum state would not be a local event. It would redefine the rules everywhere it reached. The properties of particles depend on the vacuum. Their masses, charges, and interactions are shaped by how fields settle into their lowest energy configurations. Forces behave as they do because the vacuum supports particular field structures. If the vacuum were to change, those structures would change as well. This would not be like a phase transition in ordinary matter, where ice melts into water or water boils into steam. Those transitions involve rearrangements of molecules within an existing framework. A vacuum transition would alter the framework itself. The values of fundamental constants could change. Forces could strengthen or weaken. Some particles might cease to exist, others might become unstable. Atoms as we know them might not be possible. Chemistry might not work. Structures built under the old rules could dissolve under the new ones. This is what gives the vacuum such an outsized role in determining fate. It does not need to act continuously. A single transition would be enough. That said, there is no evidence that such a transition is imminent. If the vacuum is metastable, its lifetime may be vastly longer than the current age of the universe. The barriers separating vacuum states may be enormous. Quantum tunneling between them may be extraordinarily rare. From a practical perspective, the vacuum appears stable. It has supported the universe for billions of years without change. But from a theoretical perspective, the possibility remains. This possibility arises naturally in theories that attempt to unify forces or explain the vacuum's properties. Many such theories predict multiple possible vacuum states, each corresponding to a different way fields can settle. In this view, the vacuum we observe is not inevitable. It is one outcome among many. Why this one was selected is not yet understood. It may be the result of conditions in the early universe. It may be that only certain vacua allow long-lived structures. Or it may be that many vacua exist, each realized in different regions. Regardless of the explanation, the implication is striking. The vacuum is not just a passive state, it is a choice point. Once chosen, that state governs everything that follows. This makes the vacuum unlike any other physical entity. A star can explode without ending the universe. A galaxy can collide without rewriting the laws of physics. Even space-time can curve and ripple without changing its fundamental structure. But the vacuum is different. It sets the structure. In that sense, the vacuum does not merely influence fate, it defines the range of possible fates. This does not mean the vacuum is conscious or intentional. It does not decide in the way a mind decides. The language of decision here refers to consequences, not agency. The vacuum decides fate because its state determines what is allowed to exist. This idea can feel unsettling because it places ultimate contingency at a level we rarely think about. The existence of atoms, stars, life, and observers may depend on which vacuum state happens to be realized. At the same time, there is something oddly impersonal about this. The vacuum does not favor outcomes. It does not aim toward complexity or simplicity. It simply follows the rules of energy minimization and field dynamics. If a transition were to occur, it would not be an event that spreads like an explosion in space. It would be a change in the vacuum state that propagates at the speed of the light, redefining conditions as it goes. Inside the new region, physics would be different. Outside, it would remain the same. The boundary would move, not as a shockwave of matter, but as a shift in the underlying state. Such a scenario is difficult to imagine because it does not resemble anything in everyday experience. It is not destruction in the usual sense, it is replacement. Everything inside the affected region would adjust to the new rules instantly, not because time stops, but because the very framework of time, space, and interaction would be altered. This is why discussions of vacuum stability often sound dramatic, even when presented carefully. The consequences are extreme by definition, and yet this is not a story of imminent danger. It is a story about what physics allows, not what is likely to happen. The same theories that permit vacuum transitions also predict that such transitions are extraordinarily unlikely under present conditions. The universe appears to be resting comfortably in its current state. Still, the possibility reshapes how the vacuum is understood. It is not merely a background, it is a configuration with alternatives. This reinforces the idea that the vacuum is not nothing. It has internal structure, energy landscapes, and stability properties. It behaves like a system, and like any system, it has states. The fate of the universe, then, is tied not just to matter, energy, or expansion, but to which state the vacuum occupies and whether that state remains unchanged. This perspective also changes how cosmic time is viewed. The future of the universe is not determined solely by initial conditions and known forces. It is also conditioned on the vacuum's stability. If the vacuum remains as it is, the universe will continue to expand, cool, and evolve under familiar rules. Stars will form and die. Galaxies will drift apart. Structures will slowly fade. If the vacuum were to change, the story would be entirely different. That difference is not something we can extrapolate in detail because we do not know what alternative vacuum states would look like. They may not support complexity. They may not support matter as we know it. This uncertainty places a quiet emphasis on the vacuum's current configuration. It is not just one possibility among many. It is the one that makes this universe possible. That does not mean it was chosen for that reason. It means that, among possible states, this one allows a long-lived structured cosmos. This observation sometimes leads to philosophical reflection, but physics does not require philosophy to acknowledge the fact. It is a statement about compatibility between rules and outcomes. The vacuum sets the rules. The universe plays out within them. What is striking is how unobtrusive this rule setting is. The vacuum does not constantly intervene. It does not adjust conditions moment by moment. Once established, it simply persists. That persistence is what gives the universe continuity. It allows the same laws to apply today as they did billions of years ago. In that sense, the vacuum decides fate not by action, but by consistency. This consistency allows predictions. It allows memory. It allows history. Without it, there would be no stable past to build upon. The idea that the vacuum holds such power can feel heavy, but it can also feel grounding. The universe is not arbitrarily changing its rules. It is resting in a configuration that resists change. That resistance is what gives time its direction. It allows systems to relax, to dissipate, to evolve. If the vacuum were wildly unstable, there would be no long-term processes. Everything would be subject to sudden, unpredictable shifts. The calm we observe on cosmic timescales suggests that the vacuum is deeply stable, even if not absolutely eternal. This balance between stability and possibility is part of what makes the vacuum such a compelling subject. It is neither frozen nor volatile. It is steady, but not immutable. The vacuum begins to feel less like an abstraction and more like a quiet authority. Not a ruler, not a force, but a condition that everything must respect. It does not enforce its role loudly. It simply remains what it is, and in doing so, it determines what everything else can be. The fate of the universe is not written in the stars alone. It is written in the vacuum between them. That realization does not demand fear or urgency. It invites patience. The vacuum has carried the universe this far. It shows no signs of wavering. Whatever possibilities exist beyond it remain distant, theoretical, and constrained. For now, the universe continues under the same quiet conditions, unfolding slowly, predictably, resting on a foundation that does not announce itself, yet governs everything that follows. And with that foundation in place, attention can gently turn toward the final question, not of fate or collapse, but of stillness. What does it mean to return to the quiet that is never truly still? As the ideas settle and the questions soften, there is a natural tendency to drift back toward quiet. Not silence as an absence, but quiet as a state where nothing demands immediate attention. After following the vacuum through forces, fields, pressure, energy, expansion, and fate, the mind does not need a conclusion so much as a place to rest. And fittingly, that place looks very much like where we began. Not with answers tied up neatly, but with the recognition that stillness itself is never truly still. At first glance, returning to quiet might feel like stepping away from complexity. But in the context of the vacuum, quiet is not retreat. It is arrival. It is where the activity becomes subtle enough that it no longer insists on being tracked moment by moment. The vacuum has been active throughout this entire journey, but it has never been loud. It has never rushed. It has never forced itself forward. Its influence has always been present, even when unnoticed. This is the kind of quiet the vacuum embodies, a quiet that contains motion without spectacle, a quiet that supports structure without announcing itself, a quiet that remains even when everything else fades. In everyday life, quiet often means a lack of stimulation, fewer sounds, less movement, a pause between events. But that kind of quiet is relative. It depends on contrast. The quiet after noise, the stillness after activity. Remove the reference point and the definition collapses. The vacuum's quiet is different. It is not defined by what came before. It does not follow noise. It does not wait for activity to stop. It is present even when activity is happening. This is why it has been so easy to overlook for so long. The vacuum does not interrupt. It does not draw boundaries. It does not separate itself from what occurs within it. Instead, it underlies everything continuously. Even now, as you rest and listen, the space around you feels calm. The air may be still. The room may be quiet. But beneath that calm, beneath that stillness, the vacuum is doing what it has always done. Fields fluctuate. Energy persists. Possibilities are explored and resolved within constraints so tight they rarely leave a trace at human scales. This activity does not disturb rest. It enables it. There is something deeply counterintuitive about that idea. We tend to associate activity with disruption and stillness with peace. The vacuum does not fit neatly into that division. Its activity is what allows stability. Its fluctuations do not lead to chaos. They settle into patterns that repeat, that hold, that support. If the vacuum were truly still in the absolute sense, the universe would not exist as it does. Perfect stillness would mean perfect certainty. No fluctuation, no variation, no room for structure to emerge. The quiet that allows existence is not silence. It is a restrained motion. This restrained motion is what allows particles to appear as stable excitations rather than transient noise. It is what allows forces to propagate reliably. It is what allows space-time itself to maintain coherence while stretching and bending. The vacuum's quiet is disciplined. This discipline is not imposed from outside. It arises from the rules that govern quantum fields and space-time. Those rules do not demand absolute rest. They demand balance. Balance here does not mean equality. It means constraint. Fluctuations are allowed, but only within limits. Energy exists, but only in specific forms. Changes occur, but only in ways that preserve overall consistency. Because of this, the vacuum's activity rarely accumulates. It does not build up into runaway effects. It does not drift toward disorder. It continually resets, averages out, and stabilizes itself. This self-regulation is one of the most remarkable features of the vacuum. It does not require correction. It does not require supervision. It behaves the same way everywhere, all the time, without adjustment. This reliability is what allows physics to work at all. When you set aside the details and let the ideas rest, what remains is not a sense of incompleteness, but a sense of continuity. The vacuum is not a puzzle waiting to be solved so much as a condition waiting to be understood. Understanding, in this case, does not mean pinning it down completely. It means becoming comfortable with the idea that quiet does not imply emptiness, and stillness does not imply inactivity. The vacuum is quiet because its activity does not call attention to itself. There is something deeply fitting about ending here, not with a final claim or a decisive statement, but with a return to quiet awareness. The vacuum itself does not conclude. It does not resolve. It simply continues. And in that continuation, it holds everything else. Stars burn and fade. Galaxies form and drift apart. Particles appear and disappear. Fields fluctuate. Space stretches. Time flows. All of this happens against the same baseline, the same lowest energy state, the same quiet background that never quite settles into absolute stillness. Even the expansion of the universe, dramatic as it sounds, is gentle when viewed moment to moment. Space does not tear. It does not snap. It stretches slowly, patiently, guided by the vacuum's persistent influence. On human timescales, nothing changes. On cosmic timescales, everything does. And through it all, the vacuum remains present. This presence is not comforting because it promises permanence. It is comforting because it promises consistency. Whatever changes occur, they occur within a stable framework. The vacuum does not resist change, it accommodates it. That accommodation is what allows the universe to be dynamic without being chaotic. In that sense, the vacuum is not a thing you leave behind as understanding grows. It is something you keep returning to each time with a slightly different perspective. At first it looks like nothing, then it looks active, then it looks foundational, then it looks decisive, and finally it looks quiet again. Not because it has changed, but because attention has. Returning to quiet is not a step backward. It is a recognition that the most fundamental features of reality do not announce themselves loudly. They persist. This persistence does not demand interpretation. It does not require belief. It does not ask for agreement. It simply continues, governed by rules that hold whether anyone notices or not. The vacuum does not care whether it is understood. It does not respond to curiosity or ignorance. It behaves the same way regardless. And yet, understanding it changes how everything else is seen. Once you realize that emptiness is structured, silence is active, and stillness contains motion, the world feels slightly different. Not heavier, not stranger, just deeper. The space between things no longer feels like a gap. It feels like a connection. The pause between thoughts no longer feels like absence. It feels like a background hum waiting to be noticed. Even rest takes on a different character. It becomes less about stopping and more about settling. This settling is what the vacuum does best. It is the state systems relax into, the configuration toward which disturbances fade, the quiet baseline that remains when excess energy dissipates. In that way, the vacuum mirrors rest itself, not the rest of complete inactivity, but the rest of balance. When you lie still, your body is not inactive. Your heart continues to beat. Your breath continues to move. Cells continue their work. Signals continue to flow. The system is active but not strained. That is a kind of quiet that sustains life. The vacuum's quiet sustains the universe in much the same way. There is no need to force a final insight here. The vacuum does not offer conclusions. It offers conditions. It allows the universe to exist without explaining why existence should exist at all. That question remains open, and perhaps always will. But the presence of the vacuum tells us something important. Existence does not require constant effort. It does not require continuous input. It rests in a state that supports itself. That self-support is subtle. It does not look like strength in the usual sense. It looks like calm. As attention drifts, it becomes possible to let the details dissolve without losing the core understanding. The vacuum is not empty. Quiet is not still. Nothing is not nothing. These ideas do not need to be held tightly. They do not need to be resolved. They can simply remain nearby, like a background awareness. The universe continues whether or not these ideas are remembered. The vacuum continues whether or not it is thought about. That continuity is what allows rest. And so, as the story eases back into quiet, there is no final statement to make, no boundary to mark. The vacuum does not end, and neither does its influence. It remains beneath everything, supporting motion without motion, change without disturbance, and existence without spectacle. The quiet you return to is not an absence. It is a presence so steady it no longer needs to be noticed. And within that quiet, the universe continues to unfold, gently, patiently, never truly still.